Hi everyone, welcome to our webinar for today, the 28th of April. We're just going to leave it a minute or so to let everybody file into the virtual webinar room. It often takes just, 30 seconds to a minute for everyone that's registered to actually appear as part of the audience. All right, we might kick off. So welcome everybody. We're very excited to kick off Tool Time 2, the next of the GSQ UQ collaborative webinar series. We decided to have a Tool Time 2 after Tool Time 1 just blew our socks off last year with how popular it was and how much interest we had from the geoscience community. So we've managed to pull together a really great lineup of speakers again for Tool Time 2, and you'll see all of their names on the screen here. And I just want to thank them all for being part of today's webinar. It's really great. Before we go too much further, I want to say welcome and to pay my respects to the traditional owners of the lands on which we gather, which, we're located here in Brisbane, but that could be across Australia and across the globe. And I want to acknowledge their elders past, present and emerging. And before we start on the webinars, on the speakers themselves, I also wanted to quickly highlight that our next webinar, which is again the last Thursday of the month, so the next webinar in May, will be Global Friends in Geoscience. So we're going to have representatives from various geoscience organisations and different geological surveys and geoscience research organisations around the world. But without any further ado, Karen, can you do the honours of introducing our first speaker?
Excellent. Thanks, Helen. And our first speaker today is John Bryant, and we thank John for squeezing us in because he has, we've got him going first. So if you have any questions, because he has to run, we can have a quick question or two, but we can always follow up later. So John's talking today, he's a QGIS specialist, and he's talking today about using the Geoscience plugin to generate cross sections, which I myself am really looking forward to. Thanks, John.
Okay, thanks, Karen and Helen and Evan. I really appreciate you inviting me along to this today. So I've got 13 minutes, I think, to do this, and I think I've got about 15 or so minutes of material, so I'm probably going to speak fairly quickly so I can try to squeeze it all in. But so can you see my screen there? Am I good to go?
Yes, yeah, looks good. Thanks, John.
Oh, okay, great. So my name is John Bryant. I'm from Mammoth Geospatial. We specialize in open source GIS and geospatial web applications. And today, like Karen said, I'm going to talk about QGIS and using the Geoscience plugin to generate cross sections with 100% open data from the Geological Survey of Western Australia. So first off, about QGIS, it's a free and open source professional grade desktop GIS package for mapping, analysis, geospatial data management, etc. And many mining and exploration organizations these days, large and small, are using QGIS, not just because it's free, but because it's really, really great. It has a ton of core functionality, which gets extended by plugins. And so one plugin that we're going to look at today, the Geoscience plugin, this was developed by Roland Hill here in Australia. It's also free and open source. And what it does is it uses typical downhole drilling data to generate drill hole traces and cross sections. So I'm going to do this by way of a live demo. So wish me luck. Okay, so in Western Australia, the Geological Survey of Western Australia has a massive amount of open file exploration data. It has including 100,000 historic exploration reports, and in those reports are contained 2.5 million drill holes. So we're going to use an annual report from the East Pilbara 2012 with a year's worth of drilling, logging, and assay data. So in this area over here in the East Pilbara. So, so what are we looking at here? We've got 389 drill holes and related downhole surveys, assays, and geology data. So we're going to use the Geoscience plugin to try to make sense of some of this stuff. So the Geoscience plugin, when you install it in QGIS, it gives you a set of buttons on your toolbar. It also gives you a drop-down menu. So I'm going to go through the drop-down menu in this case. And the first thing I'm going to do is get this zoom bar out of my way. How do we do that? Here we go. First thing I'm going to do is use the the desurvey holes tool to create drill hole traces from the collars layer and the survey data. So the Geoscience plugin is smart enough to identify by names. These are the layers we're looking for. It's looking for a collars layer and a surveyor's layer, so it's discovered that. And similarly, it's smart enough to look for column names that sort of match what it's looking for. So it's identified correctly what we need here. If you have different column names, you may need to set these yourselves, but in this case, we're good to go. So I'm going to click OK and run that. And I'm getting an error. Why am I getting an error? Live demo, no. Bear with me one moment. I will try that again. And let's try that again. Desurvey holes. Okay, that's working that time. That did not happen in the 7 times that I practiced doing that, but there we go. So it's running through generating the traces, and we can take a look at those traces.
John,
Yeah.
some of the things you're doing, we can't see. It's off screen. Have you got pop-up windows coming up or?
Oh, let me check that. Thanks for stopping me on that one. So let me try now.
Okay. Okay.
Can you see my attribute table?
Okay. Yes, I can see it now.
Okay, and can you see if I run that? Can you see that?
We can see it now. We couldn't see
Okay.
it last
Okay.
time. We still just saw the map.
I must have just shared the QGIS window instead of the screen. Okay.
Excellent.
So yeah,
Thank you.
just to reiterate what I did there anyway. So the desurvey hole dialog brings up the collars and the survey layers, and it's found the attributes there as I explained. So when I ran that, I'm gonna remove that so out of the way. So it's created these drill hole traces, and as you can see, they're curved. They're not just a straight line because it's picked up all the intervals in the assay files. So we've got those 3-dimensional drill hole traces projected into a 2D space. And the next thing we're going to do is we're going to add some downhole data to those. So if I just take a quick look at the geology attribute table, I can see it's got hole IDs, intervals identified along those drill hole traces. And then the column that we're looking for is this lith1 code. So we're going to get our lithologies for those intervals from this. We're going to attach them to those traces. So if I run the Geoscience drilling downhole data tool, I'm going to attach the geology information. And what I want to end up with is hole ID, from, to, and the lith1 code. And so we could actually attach any of those attributes from that table, but we're just going to focus on those ones for now. So click run on that. Just take a moment, and we end up with this new table here, colors downhole geology. And just to take a little bit of a closer look at how that works. So it's taken the attributes that we saw before, and whereas before what we were looking at was just a basic table of information, now we're seeing it. If I zoom into one of those features, I can see it's put that information onto a single interval along that drill hole trace. So that means that every interval along the traces now has an attribute. So which means we can start to apply some styling. So I've got a predefined style file that I'll attach to it. And that is this downhole geology lith1, that's a QGIS style file. And if I load that, so what it's done is it's taken those lithology codes and mapped them to a category, and given it a color. So if I click OK on that and I zoom out, I can see all those colors applied to those intervals along the traces that have those specific geology codes. So we can do the same thing with the assay data. And so I'll choose the assay table, hole ID from to, and this was an iron ore project. So we're just going to take a look at iron %. So if I click OK on that, it'll create another table, another data set, the downhole assay data set. So as we can see, just currently simple traces, but we can add the predefined layer file to that as well with the QGIS style file. So if I load that, this is the FE %, and load the style, and then we can see that it's color coded based on the iron content. So if I click OK on that, yeah, so now we can see those assays along those drill hole traces. So another thing we've done with the style file is predefined labeling for significant intervals, and that's done using a rule-based labeling in QGIS. So we've created this significant intercepts rule-based label where any feature or any interval that has an FE % over 64%, it applies this label expression. And so it's popped on just on those intervals that are over our cutoff, it's labeled them for us. So yeah, so we're ready to create a section now that we've got our traces and our downhole data associated with them. So we're going to find an interesting drill line, which we've got here. It's got a couple of significant intercepts, and we're going to use the Geoscience plugin section manager to draw a section along that line. So I'm going to do a 50-meter wide section. And if I just click on map canvas, and then I can click and drag along the map canvas to create that section. So if I do that, the layers that I want to see in the section are the assay, the geology, and the collars themselves. And then where it says elevation raster here, this is to give us a profile like of the surface on our section. It can pull those from a digital elevation model file that we've got loaded into the QGIS project here. So if I click OK on that, it'll take a moment to run through and build that section. And once it's finished, it's going to add a few more layers to the project and zoom us to that section. So there we go. So there's our section that we just generated. And what it's done is it's created a set of temporary memory layers in QGIS. It's borrowed the symbology from the downhole and the collars layers that we had already, but it's created these new memory layers which show the data in section view. So we can turn our geology on and off, we can turn our assays on and off. And one thing we can do with this, I mean, I'm not a geologist, but if I were, I might want to do some interpretation on this. So I'm going to take an empty geo package, and I'm going to add my own interpretation of where I think an ore body might be, for example. And the actual geologist in the room will be scoffing at me right now, but that's okay. I can take it. So created my yeah, so I've created my interpretation there. Right now it's a bit jagged, but if I want, I can apply a smoothing style to it. And just as a quick aside, how that's working is using QGIS geometry generators, which are super cool ways to get all kinds of interesting visual effects on your styling without necessarily having to modify the underlying data. Okay, so basically we've got our section now. I'm going to just reorder a couple of layers here so I can get it looking just like I want it to. And so I've got my interpretation with the assays on top. The last thing, what if I wanted to export this as a nicely formatted PDF? So I can use QGIS's map templating functionality. And I'm just going to grab the name of this section there. And I'm going to create a new layout from my cross-section template. And I'll call it based on the name of the section. And so it's popped it up. I've pre-configured this layout. It's got the map frame, it's got a title. We've got a legend that we need to do a little bit of tidying up on just by removing the sections that are not relevant. I'll do this quickly and hide that, hide that, hide that. So we've got a legend, and then I've got a significant intercepts table, which we need to do a couple of quick updates to. We need to make sure it's pulling from the correct assay table. We need to clean up our attributes, and so this will be whole ID from to, and then our X-ray FE percent. And so now we've got a nice, basically we've got a nice layout here that we can export to a PDF and print off or email around. The last thing I would do, but I think I'm probably running short on time, is I would go back into QGIS and shift these labels around so they're not sitting on top of each other, but that is, I'll leave that one to your imagination. So just to wrap up, that's the Geoscience plugin. It's got some really cool functionality, and you can generate cross sections, as you can see. It's the future of the plugin is it's going to be superseded by the looks of it by a new plugin that's in development called OpenLog. This is being developed by Icelandia in France, and this will do a lot of the same stuff plus more, plus strip logs and more 3D visualizations. So hopefully we'll see a first version of that coming out in the next few months. And yeah, so again, I'm John Bryant from Mammoth Geospatial. We're on a mission to help organizations use Open Geospatial. We're always looking for talented and passionate people to help us on this mission. So please get in touch. Thanks a lot.
Thank you very much, John. That was great. I have to say, I haven't used QGIS myself, so it's good to get a bit of a feel for the capability of the software. So we don't have any questions just at the moment. But and I understand that you have to run. If anybody wants to get in a quick question, please pop up quickly. Otherwise, we'll let you head off to your next class. And if any questions come through, we'll send them along afterwards.
Sounds great. Yeah.
I think we've mostly got comments on the geological interpretation. John?
Well, yeah, I'm not a geologist, so.
But there are, if you've got time, I think there's 2 questions. And remember, everybody, can you put your questions in the Q&A rather than in the chat? It helps us figure out what's a question and what's commentary. Mike Whitbread is asking, how many drill holes can you squeeze into a section before performance becomes an issue? Oh, that's a great question. So the answer is I don't know. I mean, in that case, we're looking at a pretty small number, I think about a dozen, but I don't know. I would give it a shot. I mean, it took about 10 seconds to generate it with that many drill holes. It's almost instant if you do it with a simpler trace. So I think it's partly to do with the density of the downhole data as well. Yeah, your mileage may vary. And Peter Ray also would like to know, how do you turn off the section? Yeah, okay. I can take a second to show that. And then while you're showing things, Steve and Moore would also like to know, where do we find the QGIS plugin?
Right. So the to turn off the section, so the way that the Geoscience plugin does this is it dumps it onto a different, like a remote part of the QGIS canvas. So if I actually zoom out, you know, basically this just becomes part of your coordinate space, but it's way off. It's way off in a far away from the rest of your data. So if you want to get back to your normal two-dimensional data, you can zoom to the layer of your section plan, for example, or zoom to any of your other layers, and then you can to get back to your section, you can zoom back to that group. So basically it's a matter of navigating to and from them. And then in terms of turning visibility on and off, yeah, you can just turn them on and off using the regular layer controls. To get the Geoscience plugin, hopefully that answers the question.
I think we're going to run out of time because there are about 10 more questions now.
Okay. To get the Geoscience plugin, go into QGIS, go into plugins, manage and install plugins, and you'll find it. It's among the plugins that are available there.
Why don't we, Karen and I can take a copy of all of these questions and the people who are asking them, and if you could provide answers, John.
Fabulous.
Then we can get back to the list of attendees and let them
Certainly,
know.
yeah. Send them through. I'm sorry I can't stay longer. I have to give a training session in 7 minutes, so I guess I better go. Thanks for accommodating me. Yeah.
We better let you go.
Okay.
Thanks again, John.
Okay, take care. Cheers. Bye.
Thanks. And our next presentation is actually somebody from based at UBC in Canada, in Victoria, Vancouver. And Lindsey Heagy has a colleague, Craig Miller, who's also here online to answer questions, but it's the middle of the night for Lindsey, so she couldn't join us in person. Rick now will start her presentation on using SimPEG.
Hello, everyone. Thanks for taking time to join today. I'm delighted to be here representing the SimPEG team as a part of this tool time session, and I'm very much looking forward to hearing about all of the amazing work and open tools that are being shown off today. So I'm Lindsey Heagy. I'm an assistant professor at the University of British Columbia in the Department of Earth, Ocean, and Atmospheric Sciences. And today I'll be sharing some of the work we've been doing within the SimPEG community, developing open source tools in Python for simulating and inverting geophysical data. So I want to start by acknowledging where I'm joining you from today. So I'm joining you from across the Pacific in Vancouver, BC. And UBC in Vancouver is located on the traditional, ancestral, and the unceded territories of the Musqueam, Squamish, and Tsleil-Waututh First Nations. So if we start off by taking a look at the problems that we're looking at, we're looking at solving inverse problems. And so given data that are measured over the Earth, so on the right, we've got an image here, for example, with electromagnetic data. So these might be electrical or magnetic field measurements over the Earth. Some estimate of noise level or uncertainties associated with those data. And the ability to forward model. So in the example of electromagnetics, we need to be able to solve Maxwell's equations. The goal of the inverse problem is to find an Earth model that gave rise to those data. So in the case of electromagnetics, we would be looking for a subsurface model of electrical conductivity that's consistent with the data that we've observed. So the inverse problem is ill-posed. It's non-unique, which means that there are many potential models that could fit the data, and it's ill-conditioned. And so any inverse problem and any approach to solving the inverse problem must address these issues. And so this is where it becomes really important, and there's a lot of interesting research being done and yet to be done on how do we actually bring in additional information into the inverse problem. So this could be things about the geology, if we've got borehole information, perhaps we can build up a reference model, maybe from another geophysical data set, or maybe we've got physical property measurements, so we could put bounds on the physical properties that we expect to see. So there's many other sorts of data that we might be able to sort of take advantage of and try and use to constrain what we're getting out from the inversion. And so we need a framework to solve the inverse problem. And there's, broadly speaking, two approaches, or sort of two classes of approaches that can be taken. So a Tikhonov approach is deterministic. We formulate the inversion and the inverse problem as an optimization problem, where we try and fit a data misfit and a regularization term that are weighted with some trade-off parameter between them. Another class of problems is a Bayesian approach. And so here we want to characterize, we bring in prior information, and we want to find a solution that maximizes the posterior. And so in this case, what we're going to do is we're going to be taking the deterministic approach. So Bayesian approaches, you might think about using sort of MCMC style work. Within the SimPEG community and the work that we've done, we'll take a deterministic approach. So this optimization problem that we pose here on the left is the one that we're going to be solving. And so there's a few pieces to this, is what we start off with. So we've got this flow chart here on the right, is we've got our field estimates, our field observations and estimates of the error. We need some ability to forward models. So within SimPEG, we have tools for building up meshes and solving partial differential equations. Might also need tools to build up a reference model or sort of incorporate that prior information, for example, into a regularization term. Then we go ahead and we define that optimization problem comprised of that data misfit in a model norm term. And there's different ways that we can actually design the model norm. And then there's perform inversion. So there's a few different styles. For example, in EM, we often use what's called a beta cooling strategy. So we start off with a lot of weight on the regularization to try and get a nice smooth model. And then as the inversion runs, we'll try and fit the data progressively more and more. Then at the end of the day, we get out a model and we're going to interpret that in light of the geology and what we know. And so often this is an iterative process, and you're going to go back and reevaluate each of the components here and perhaps tune parameters, rerun the inversion. And each of these kind of really requires, thinking through and different styles of expertise. And so one of the values of working in an open source space is we're able to really leverage knowledge and ideas and expertise from people in different spaces. And so I won't go in depth into this framework here today, but if you are curious in doing a deep dive into inversion, there's two talks. So Doug Oldenburg gave a talk on the fundamentals of inversion. And then I gave a talk about how we actually take this framework and really sort of work through the details of SimPEG as a part of the MTNet seminars. And so you can follow that link below if you would like to take a look at those. So the goal of SimPEG is to solve inverse problems. So working through each of the components of that framework that I just showed you. And really, with any code base that's developed, any open source project, open or closed, any coding project, sorry, open or closed, is going to require that you choose your priorities. And so within the SimPEG community, what we really want to do is facilitate research in geophysics. We want people to be able to go in, explore the different building blocks, plug in new ideas, and have those be available to manipulation. We want to be able to have the code be declarative. And so that by that, I mean, easy to read. When we write down the code, it should look like the math. And this is really quite valuable, especially in educational settings as well, where you want to actually use the code as a tool to learn about how we solve these problems. Extensibility is critical when we're talking about research, is we want to be able to, plug in new regularizations or maybe come up with a new strategy for a joint inversion, but not have to rewrite everything from scratch. And then I think a common thing that many folks here today will be talking about is really the value of an open community, is being able to look into the code, see what's going on, but also have the code base be a space for collaboration where we can learn from and leverage the knowledge of others. So rather than kind of giving you a deep dive into SimPEG and all the functionality, I want to just give you a bit of a flavor of a few different examples and work that's been done. And so this is by no means comprehensive. It's very much meant to give you just a bit of a sampling of some of the work that's been done within the SimPEG community. And so starting off with a couple examples in potential fields. So we've got gravity and magnetics both plugged in. We also have magnetic vector inversions, and these can be run in Cartesian or in spherical coordinates. and also sparse and compact norms. So Dom Fournier deserves a lot of credit for developing both the MVI inversion as well as the implementation of sparse and compact norms. And the example that I show you here is an inversion at the Kivitsa deposit, looking for the magnetic vectors. And then from that, actually seeing if we can learn something about the tectonic history. On the right, I'm showing you some images from a paper that's hot off the press by Craig Miller, who's hopefully able to be joining us live for this session and might be able to answer some questions afterwards. So he's been looking at, in this case, using both gravity and magnetic data to come up with an understanding of a volcanic setting. And so this paper is quite interesting as he explores different avenues for using the reference model. And so if that's something you're curious about, I encourage you to take a look. We also have capabilities for electrical and electromagnetic methods, both in the frequency and in the time domain, as well as for controlled sources or natural sources. So for example, if you want to do magnetotellurics. We have 1D, 2D, and 3D implementations. And so the example that I show you on the bottom here is work by Sagi Kang. He's a postdoctoral researcher at Stanford and one of the SimPEG founders. And so he's been doing a lot of work with airborne electromagnetics in California to characterize groundwater systems. And so the example here that I show you makes use of the EM1D code, the time domain code, and also makes use of sparse and compact norms. And so although that was first implemented for potential fields, because of the modular nature of the code base, can be brought in and connected with the electromagnetic implementation. And then on the right, I'll show you just a quick example of some of the work I've been doing, looking at electromagnetics in settings where we have steel-cased wells. And so steel is very, very conductive as compared to the background, and it's also got a substantial magnetic permeability and a very strange geometry as compared to the geology that we're working with. It's very thin, very long. And so trying to design a mesh where we can really highly accurately model this can be quite challenging. And so here we work with the cylindrical meshes. And then the final sort of set of examples that I'll show you is joint inversions. And so again, this kind of comes back to these ideas of a modular extensible framework, is now that we've got each of the different physics implemented, there's space to start playing with combining different geophysical data together and using different strategies to couple, for example, gravity and magnetics or electromagnetics. And so the example that I show you on the bottom here, on the bottom left, is work that's been led by Jaja Sun's group at the University of Houston. And so they've implemented cross gradient and then are actually using the physical property cross plot that comes out to then come up with a geologic or a quasi-geology model based on the physical properties there. And then on the right, showing some work that's been led by Thibaut Astic, to bring in petrophysical information into the inversion. And this is through the Petrophysically and Geologically Guided Inversion Framework, or PGI. And so with this, we want to fit the geophysical data as well as reproduce the petrophysical data. And that is what we're using to tie together or to couple different physics. And so with that, we build a quasi-geology model as a part of the inversion. And so this paper that I linked to up top explains and works through the framework there. And so both of these are implemented within the SimPEG framework. And so finally, wanted to point to a few educational resources that have been built with SimPEG. I think this is so important as we're talking about, the role and the use and usefulness of geophysics, is it is a tool. It's one tool that's part of solving a geoscience problem. And so we need to be able to communicate and connect with collaborators in other fields. And so educational resources can be a really valuable and useful conduit to explaining what's going on. And so the Geosci XYZ website is one that we've been working on to develop open access textbooks for undergraduate geophysics as well as for advanced electromagnetics. And so the geosci.xyz site actually makes use of SimPEG to build up quite a number of the examples. And one space where we made use of this is a Geoscientists Without Borders project in Myanmar. So we built up Jupyter notebooks, basically apps that people can use to load up data, visualize those data, and explore how to invert these data to locate potential aquifers that could be drilled for drinkable groundwater. So finally, I want to share a few resources for you. Got links for the documentation. There's a community forum, as well as a Slack chat channel. And recently we've been launching a seminar series. So if you're curious to see just different things that people are doing with seminars, or sorry, different things that people are doing with SimPEG, I'd encourage you to check out the seminars page. And so with that, I will say thank you very much. And a big shout out to the SimPEG team. I showed some images of them here. All of this work builds upon the great work that is done by this community. So thanks so much.
Excellent. Thanks very much to Lindsey for taking the time to do the video, given that she couldn't be with us, and to Craig Miller for joining us for today's session. And do we have any questions coming through at the moment? I think they're all the previous ones. We can give it a minute or two. But Craig, are you able to stay on for a little bit longer? See if any questions pop up, we can no always pass those on and answer them. But that's a great tool, and really interested to see. I'll definitely follow up and have a look at a couple of the papers, because I've been talking to some colleagues about potential for joint inversions. Excellent. Well, thanks for your time as well, Craig, for joining us.
No problem. Thank you.
We'll move on now. Our next speaker is Tim Hall-Johnston. I was about to say Johnston Hall. Sorry, Tim. And he's with Searcher Seismic and GeoClerk, and he's going to look at improving searching with GeoClerk. I should just clarify, most of our talks here are open source software, but in this case it is not. It's a commercial product with Searcher, but several of us have been having conversations with Searcher, and we thought it's worth flagging this tool to everyone today. Thanks, Tim. I'll hand over to you.
Thank you, Karen. Thanks very much for having us here today. Let me just share my screen. Yeah, I should point out that, yes, as Karen said, this is a commercially available product. It's an off-the-shelf, ready-to-go product. And I'm going to spend today really just kind of running you through what it is and some of the features, because it is a relatively new product to the mining space. And hopefully we can get through some of the features and then do a bit of a live demo depending on time, as we are a bit time limited. Look, GeoClerk is a tool that was built around the idea that a picture says 1,000 words. As geologists and geoscientists, when you're searching through documents, you tend not to read documents top to tail, but you look for the interesting imagery. There's so much value in the images that can be found in documents. And GeoClerk really is a tool that is built around, searching documents. So when we talk about search, we talk about that, often laborious project of running through and reading and identifying all kind of key information that may be in particular documents. So GeoClerk is, built around, a picture is worth 1,000 words. And that's because there's so much value in geoscientific imagery. There's no cheap way to run any kind of survey, whether it's seismic, gravity, magnetics, etc. And as you all know, all of the data from those surveys culminates in some kind of visual representation, whether that's a 3D model or some geophysical imagery or geochemistry overlaid on a map, or sections that have been built out of QGIS, as we've seen just before. So really getting to the bottom, getting to those images is the quickest way to kind of get value out of a lot of these documents. And we find that geologists and geoscientists tend not to read documents top to tail anyway. If you pick up an exploration report or a relinquishment report, you tend to flick through it, look for an interesting section or some interesting geophysics, and start reading from there. So, this is a tool that's been built to kind of help you navigate in that way that you kind of like to with documents anyway, but by bringing them to the front. And to do that, GeoClerk has a machine learning classifier behind the scenes. So it's essentially pre-reading all of the documents for you, finding the images and then classifying them into their kind of relevant categories that you would be looking for. So it knows what a 3D model looks like, it knows what a line of seismic looks like, it knows what a map with some geochemistry on it looks like, etc. So that if you're just looking for, say, sections that may include certain indicator minerals, you can pull those up and find them without having to flick through too hard. So yeah, what does this mean in the end? You end up with a nice kind of pre-categorized search interface, where you're searching through all databases. If you're just looking for particular image types, you can pull those up. So if you're just looking for sections, or if you're just looking for geophysics, where something may be buried on page 300 of a document, you can jump directly to it and see the image itself rather than having to flick through those pages to get there. GeoClerk is available as a petroleum product and a mining product. So, we have different kind of image categories that you're looking at there and that you can inspect at. You can see the tabs across the top here for, oil and gas. You're looking at kind of deeper stratigraphy. So you might be more interested in well logs and structure maps rather than geophysics, etc. So it is available in both a mining and a petroleum version. Look, it's very simple as a text search engine. You can search for the province or basin or ore body deposit that you're looking for, scroll through the images, and then from any of the results, you're jumping directly into a report. And importantly, you're jumping directly to the page that the interesting imagery or figure or table has come from. So it saves you a lot of time in scrolling down to find the pieces of what's interesting, rather than having to do it yourself. So there's a text search that way. There's also spatial search. So we have a browser extension that integrates with all of the kind of GeoSurvey mapping tools. So you can search directly from GeoResGlobe, you can search from MinView or Strike. Whatever the bounding box that you set up on the map is, you can just run a search and pull back all of the imagery within the documents, all of the documents, all of the tables, all pre-categorized, ready to go within GeoClerk quickly and easily. One of the nice things with GeoClerk in doing this is that it allows you to search cross borders. So we have all of the WAMEX reports in, all of the GSQ reports in, etc. So here we run a quick search across the Cooper Basin, and we get the results from GA, we get the results from GSQ, from GEMIS, and SARIG for South Australia as well, which is good to do. So that is running a kind of bounding box spatial search across the documents. You can also input complex polygons. So if you have a particular tenement area or application that you're looking at, or somebody's come to you with a business development opportunity, you can throw their permits in as well. The nice thing about this search is that it will go through and give you results in terms of spatial relevance. So if you go and run a search on GeoView or one of the GeoSurvey sites, you may get back thousands of documents. A bunch of them are regional studies, may not particularly be relevant. GeoClerk orders things in terms of spatial relevance. So how large the intersect of your polygon is with the document, and calculates it that way. So it's quite a nice way to do it. It also allows you to, we can search for tables or figures in GeoClerk, so you can kind of interrogate or look for indicator minerals in historical assays, within tables that may have been scanned and aren't necessarily able to be OCR'd previously. From that, any images that GeoClerk has recognized as a table, you can digitize directly on the fly back from the image into a digital format. So you can either copy and paste it or download a CSV to work with that data digitally directly from the GeoClerk interface. In terms of content that's in there preloaded and ready to go, all base users get access to the public internet. So it's following all of the kind of 1,800 publicly listed companies across the ASX, TSX, and AIM in the mineral space, and a similar one in the petroleum space. So all of the operating reports and everything that goes out is automatically ingested there. There is a web crawler that allows you to go and add content in from the web, anything that's kind of open file or publicly available. And we've got plugins that have pulled in and process all of the Australian kind of GeoSurvey exploration reports. Nothing's for the offshore stuff, less interesting for sustainable mining, but the WAMEX reports are in, the DIG library is in, GEMIS is in, GSQ's library is all in, which was nice and easy thanks to GSQ's new API. SARIG and Victoria, GSVs for Victoria, and all of that importantly is georeferenced. So all of the documents are tied back to the tenements that they were submitted for. Some of the state surveys, you can use that facility out of the box, but where the information wasn't provided, the GeoClerk team has gone and linked it all back to those tenements so that you can do spatial search across all of that. GAs, publications, GSWA's, eBookshop, GSV's publications are all in there and searchable too. And there's a growing list of kind of content partners that range from organizations to scouting organizations, etc., whose content is coming in and becoming searchable. As I mentioned quickly, you can search the web yourself. So if GeoClerk doesn't have the content, some content in there for you, or if somebody comes to you with a business development opportunity, the first thing geos tend to do is go and search on the web and see what's been published about it before. This leads you down a bit of a rabbit hole in terms of finding what documents exist and then having to download them all and read through them. In the instance that you're really just interested in any of the sections that may have been published, a quick search on GeoClerk to process 100 documents that have been published on a particular deposit. In 5 minutes, then you can just pull up a list of all the sections that have been in all of those documents, rather than having to download them all, read them yourself. And GeoClerk also allows you to search through your own documents. So if you have a large technical library that's not very well structured, it's a great way to throw your content in and make it searchable. We have a client that we recently published a bookshelf for. They had a bookshelf full of conference proceedings that was stashed on DVDs and USBs on a shelf in the office. It wasn't even on a file system. And that was just taken in, pre-processed, and now they have access to this huge technical library that's very searchable. So all content that goes in, from your organization goes into a private and secure bucket. It's very easy and quick to do. So we'll jump into a demo in a sec, but if anyone is interested in more information or wants to get hands-on themselves, we do offer a free week trial for you to come in and see how it is. So if you'd like to do that, just email sales@searcherseismic.com. I'm sure the details will go out afterwards. We've got a couple of minutes left, so we'll just jump into a bit of a demo. I think it all kind of makes sense from what I've said, but what this allows us to do is, if we just search for, say, the Addervale Basin, which is getting some interest for sequestration and also some gas. It's quite a deep basin, but if we search for any kind of term, you can see the results here quickly and easily. Everything is kind of pre-categorized. Oh, this is a mining one. Let me do Olympic Dam or Ernest Henry. So I should have pre-thought of a Queensland deposit for you guys. But look, so if we're looking through it, we can see everything's kind of pre-categorized. We get a huge amount of results. Everything is coming up in real time. From any of the results that we can see, we can flick through into categories for them. If we want geology maps around Ernest Henry, we can pull those up. From any of these results, we can double click to zoom an image to get a better understanding of what it is. We can jump into the source document, just by clicking the source. And as I said before, it's landing you at the page that the image has come from, rather than on the front page of it. For any of the results, where we have spatial metadata, there is a quick spatial view where we can look at just where in Australia the result has come from, or what the spatial block associated with it is. And we can see a bit about everything here. So I think as you saw, everything is kind of categorized into its relevant image types. For maps, we have a whole different bunch of maps. If you're looking for maps with geochemistry on them, or generic maps. Rocks, we have at a bunch of different, photos, we have rocks at a bunch of different zoom levels. Geophysics, we're bundled into any of the geophysical imagery is there. Sections, again, any sections are easy to find. One of the nice things is that you can then interpret or interrogate sections for minerals, etc. We find chalcopyrite in those sections and then look them up. But yeah, I'm just running out of time. So if you're interested in any more, please just get in touch and we can get you guys set up and you can see how it is working yourself.
Excellent, Tim. Thank you very much for taking the time to join us today. I'll just double check whether we have any new questions come up, but I don't see anything in the questions of the chat at the moment. Are you able to stay around for the rest of the session for discussion, or do you have to run off?
No, I can. I'll stay around to the end. So if there are any questions, please just send them through.
Richard Blewett is asking about the fees. Is that a quick one, or do you want to discuss that with him separately?
Or why don't you touch back? Yeah, any kind of sales related questions, send them through to sales@searchofseismic.com. But yeah, it's an annual subscription and the fees are based on the number of seats that you require and then which databases you'd like access to. The more seats and the more databases, the cheaper it gets.
Excellent. Thanks very much. Yeah. Our next speaker this afternoon is Kate Wathen-Dunn, and she's a data scientist at the Geological Survey of Queensland. She's going to talk to us about accessing data from GSQ's Open Data Portal using the API. Thanks very much, Kate.
Thanks, Karen. I'll just pull up my screen. All right. Now that I've lost the rest of the meeting, can you guys see that? Yep.
Yes.
Okay.
Yep. That looks good.
Right, that little bit there, okay. Away. So I guess I'm going to reveal some of the magic behind the curtain of how Tim was able to get some of the data that he got from Queensland into their GeoClerk system. So when we did our data modernization about 1.5 years ago, one of the things that we implemented was a system that's accessible via an API, which means you can do it programmatically. And so I'm going to talk to you a little bit about that today and how you can access the data and filter it. So I'm going to cover our GitHub site and just to show you where that is and what sort of things you can find in there, because it's a really good source of information and it's a good place to start with any questions that you have. So we've tried to answer a lot of the questions that we get. There's example scripts and there's example things there. So please do have a look there. A little bit of an introduction to the Open Data Portal, though I'm assuming that everybody's seen it by now, but it's a good intro into what an API is because it works in a very similar way. We're going to talk about using filters in the API to help you with your search, and then we're going to talk about how to download data programmatically in bulk. So GSQ has a GitHub site, and within that we have quite a few repositories. And this is the main one. This is the main page you land when you search for it. And within that, we've got maybe 3 key ones that I think will be the most interest to this group. So we've got a data catalog. So that tells about all the things that we've got available online, all our open data. You can have a look through that. We've got some information about the vocabularies. So part of our data modernization process was that we standardized a lot of the way that we work in a lot of our systems. So when we talk about a particular term or we use it, we have that defined very clearly in our vocabularies. And you can look that up and you can see that when we talk about this, this is exactly what we mean. But the one of interest today is the Open Data API. So this explains a lot about how to interact with our system using the API. There are examples there. There's lots of descriptions and some scripts there too. So that's another good one to have a look at. All right, so as I said, our system is set up to access all the open file data that we hold. So about 95% of the data held by GSQ is now open file and available online. 95% of our open file data is available online. Our data is stored as data sets, so it's the way that data is packaged together and searchable. And any documents associated with that data set are called the resources. So this would be the files attached to it. So maybe you have a report and it might come with a LAS file and a CSV or things like that. So the LAS file and the CSV are the resources to the data set. So this helps you to understand how the data is structured. It'll help you find it. All our data sets are tagged, so that makes filtering really easy. And there's lots of ways you can search for it. So if you go to the Open Data Portal, this is what the landing page looks like. And in the bottom section here, you can see that we've got some pre-filtered data groupings. So it might be a type of data that you're looking at. So you can click on that and go through the steps to find what you're after. So we have quite a lot of search filters to narrow down what you're looking for in our portal. You can search on any search term, a keyword or an attribute. You can use and or. You can use, if you know a particular persistent identifier or a name. We've got a Solr query built in underneath. So if you know how to use that, and there's, like I said, there's information online that helps you narrow it down as well. You can search by data type, or if it's a particular commodity that you're interested in, or a region. So you can set up a bounding box and return any of the information that's held about that region in there. It might be a report type, or an earth science data category, or a data format even. So any of these ways you can search in our Open Data Portal just by clicking on the facet in the boxes there and narrowing your search. And the great news is you can also do that via the API. So it uses exactly the same search filters. You can search for, you can open and download data directly with the API. The only difference is that the data sets are called packages, and that's just a historical thing, just something to be aware of, that it's a little bit confusing to begin with, but data sets and packages are the same thing. And this is a really great way of automating your searches. So this is something that I'm assuming Tim does on a regular basis, where just checks to see what new data is being added to the portal, and you can automate that so you don't actually have to do it manually. And as I said, all these examples and information and ways to work with it all on our Open Data API GitHub site. All right, so I'm talking about an API. What the hell am I talking about? So an API stands for an application programming interface, and it's basically a software intermediary. So when you send requests, it handles the request and sends it to the portal, and then takes the result that the portal sends it and formats it back to you. So it's probably something that you're already using, you just maybe not consciously. Why would you bother using it? Well, it's quicker. If you get it set up right, it's pretty quick. You can automate it. You can check for data sets that are new or that have been changed or added. The data is returned in this JSON format, which is really good to be able to pass it automatically or programmatically. So it makes automation much easier. And you can also use API calls in a Python script or in a Power BI as a data source to download these bulk data as well, or to access it. So how do you use it? So apart from using it in a script or in the Power BI report, you can also write it directly into your web browser. So if you're going to do that, an API query has 3 parts. So you need to have the portal address, you need to tell it what kind of result type you want, and any filter information if you have that information. So that's our portal address, and that's what you start it with. And then after that, you would add the result type. So it might be a package that you're looking for, or it might be a search for a particular data type. So you add the result type that you're after. And then after that, if you have any filtering information, so maybe you're after a particular report or a particular type of data or whatever, and you can join multiple filters together using the AND or that %20+ symbols. So that allows you to make a really specific filter query to return just exactly what you're after from the Open Data Portal. So when you get it back, if you type it into your browser and you hit send and you get this gobbledygook back. It's just a big clump of text. But if you have an extension in your browser, you can format the JSON that makes it really easy to read and to search through. So I highly recommend that. If you're working from your browser, you can copy and paste what comes back to you in the JSON format into a text file to save it, or you can, if you're working with it from a script, you can save that JSON file directly. So here are some examples. This is what they look like. This is the sort of thing that you would type directly into your browser or use in your script. So you can see that it looks like a link. There's the web address at the beginning, and in the middle is the kind of result that you're after. And then a few of them have filters. So if the data set's about boreholes, has the borehole filter at the end, or the specific report has the type, which is the report, and the particular ID for the report at the end of that as well. So you can see that you're asking for very specific things. As an example at the bottom there that might be of interest to people, if you're looking for a particular type of report, made open file since a particular date, all of these things, like I said, you can really narrow down and specify the kinds of results that you're after. So the benefit of that is for bulk data downloads. So if you're using the browser, there's a maximum of 1,000 results returned. And if you don't tell it you want at least 1,000, you'll only get 10. But if you use it in a Python script, you can use limit and offset or rows and start to paginate the results. So you loop over the pages to get more than 1,000. You can get as many as are in there. We also have some Python scripts available, some example ones on our Open Data API GitHub site. So please do use those and yell out if you get stuck. So just in summary, the GSQ has undergone this digital and data modernization process, and now more than 95% of our open data is stored in the cloud, and it's searchable and accessible to industry. So the Open Data Portal is a great way to search for data of interest. It's accessible via API calls, and you can quickly search and download bulk data of interest. And if you have any questions or you're looking for instructions or examples, they're all available on our GitHub repo. And that's it.
Excellent. Thanks very much, Kate. Now we did have one quick question that David jumped in and answered very quickly, just confirming that all the API data is free. Any other questions at the moment? If anybody wants to jump in quickly with another question for Kate while she's here. Otherwise, we can move on and come back at the end. Thanks, Kate. That was great. You've got us caught up a little bit there. Our next speaker is Michael. Sorry, I've lost my place. Michael Rodda from Caldera Analytics, and he'll showcase how to use open file data in Python. Thanks very much for joining us this afternoon, Michael.
Hey, thank you. Can you see it all right?
Yes, that looks good. Thanks.
Okay, so yeah, my name is Michael Rodda, and I'm going to be going over some of the open file machine learning projects I've done in Python, showcasing some of the applications. So to start off with, I guess, when you're talking machine learning in geoscience, especially mineral exploration, you're almost always going to be dealing with open file data. So this is just the nature of machine learning. Most of your models are going to need a lot of training data to be able to generate something of value to mineral explorers. And I think anything outside of maybe machine learning assisted resource modeling, you're not going to have enough internal company data to train the models. So you're always going to need to go out to the public data sets. And this unfortunately has a problem in that working with open file data has a high data quality control cost that I think is consistently underestimated by all of us in the industry. So through my company, Caldera Analytics, most of the machine learning problems I work with involve the pre-drilling phase of mineral exploration. So typically you're going to be working with those inputs on the left, maybe magnetics, gravity, running it through a deep learning model to predict your basement lithology. You could just be using magnetics to predict the depth of basement, or you could be using all the surface predictors to see where outcropping basement is or predict the surface lithology. But the problem with working with open file data is you're always going to have a fixed resource cost that you can allocate to building your training data set. And so you can go down two roads. You can either go down the road of really thoroughly cleaning your data, and so you have a small training data set that's fit for purpose, or you could try and go for a bigger data set, one that will allow you to use more powerful deep learning models. But then typically I find that if you go down that route, you run into a garbage in equals garbage out scenario. So generally, all you can really do is run with these small curated data sets, but that restricts you to some of the simple machine learning models like random forest, XGBoost, support vector machines. And my personal opinion that some might disagree with is you just don't generate really valuable insights that are worth anything to mineral explorers with these simple models. So that paradox of open file data has led me into what I've really focused on in the past year, which is what's called self-supervised deep learning models. So traditionally, when you're training a machine learning model, you need a lot of labeled data where you know the outcome, and you train a model to take the inputs and predict the known outcome, and then you train that model to go out into the unknown. Self-supervised deep learning is this new technique that's really kicked off in the past 3 years that's achieved amazing results with very little training data. And that involves kind of warming up one of these deep learning models on all your unlabeled input data, saving it, and then down the track, you fine tune that saved model on your specific target or answer you're trying to do. And when I first started noticing the research, I immediately thought, you know, what domain has an enormous amount of unlabeled data? And in mineral exploration in Australia, we're so lucky to have so much data to work with. And so self-supervised deep learning is perfect for this, where it solves that paradox. You can run powerful deep learning models by using self-supervised models, and then you can put all your resources into a much smaller data set that is actually fit for purpose and capable of training a model that will then generate very rich insights. I do want to touch upon the Python deep learning toolkit. So typically when we're talking Python and geoscience, a lot of the tools that come up, and the really good tools, are more tailored towards replicating the existing geologist or geophysicist workflow. With machine learning, geoscience, it's a bit different. It's all about being the jack of all trades. So these libraries are really all you need to be able to train powerful models. And for example, Raster and Verde allow you to intuitively create grids from maybe the ground gravity databases really fast, because the problem is you're moving things, you're editing the data, you're regridding the inputs. You can't wait for Geoscience Australia or your geophysicists to generate another Australian-wide compilation again and again and again. That they're going to get annoyed. So you have to do it yourself. So there's 3 applications of these deep learning models that I want to talk about. All 3 involve using self-supervised deep learning models. All 3 have really small training data sets where we focus more on curating that small training data set. And all of them are either 100% or 99.99% using open file data. So the first one is a project I did with Oz Minerals last year, and I thank them for allowing me to briefly touch upon this. So their line of thinking was deposits are statistical outliers. They occur in strange and poorly understood areas. How can we find those areas within the Mount Woods region where their prominent hill IOCG deposit is? So the way I approach this using open file data science is first warmed up deep learning model and all the input magnetic and gravity geophysics around Australia. Then the next step was to train a probabilistic basement interpretation for 9 high-level lithological groups around Mount Woods. This was only using the Mount Woods regional drilling. So although we're using a deep learning model, we're only running about 300 to 400 data points. And how I answered that question was actually, if you take the maximum probability for a target area across all of those 9 groups, if there's an area that has a low maximum probability, it means that area and its geophysics the model hasn't been able to slot it into those 9 groups. So you could argue that that's a like low confidence area. The model's never seen that type of geophysics. It's a bit of a strange, unencountered area for the Mount Woods region. And what's a really good outcome for this is that if you look into the top left area, you have a very dark patch that corresponds to one of these low probability areas. That's the Cooper-Pedy Ridge, quite geophysically distinct from the Mount Woods geophysics. And the model has never been trained or seen this area. So relative to the Mount Woods domain, the model is saying that this new area is quite strange compared to it. So the next application, this is a project that I just finished. It was part of the Collaborative Exploration Initiative that I did with Strategic Energy Resources. So SER have 2 projects north of the Mount Isa Inlier. They're greenfields areas, there's limited drilling, and there's a lot of younger cover, really complicated things. So how do you build a deep learning model? In this case, I was once again doing basement interpretation. But how I went about it was using self-supervised learning, once again, to warm up a deep learning model, and then really focus the resources on the training data set to create a training data set where there's only 6 lithological groups. All of them corresponded to some aspect of IFCG exploration, and every single training point went through and made sure that it was corresponding to the actual input geophysics. And this was a very laborious process. So these are very fresh results, so I can't talk about the good stuff like the hydrothermal magnetite targets, but I can show the fell-stick intrusives predictions for the Ice North project. So on the left, the 2 left images, they're the inputs. The third one is the probability for the fell-stick intrusives. And the last one is this new technique measuring the model uncertainty using what's called Monte Carlo dropout. And what's really cool is that independently of this project, there was 2 recent drill holes done by Red Metal that confirm the model prediction for one of those fell-stick intrusives. So that was a really good outcome. And lastly, this is a complete left field application. It's not to do with actual exploration. It's more, how can we speed up the data cleaning process? So I was thinking, how small of a training data set can we go, but still use deep learning models? And one issue I find is when I'm generating gravity grids from the Australian National Gravity Database, it does require a lot of quality control. Shown on the right is a grid generated using the Verde package, just out of the box without any cleaning and low regularization. And you see north of the, in New South Wales, there's some new survey that needs to just be leveled a bit before regridding. So can we use deep learning to predict those areas? So yesterday, I just did a very quick, lazy 10-minute job of going around in QGIS and clicking through areas that I know from experience in the current Queensland database, where there's areas of gravity surveys that need to be re-leveled properly or excluded. And also that New South Wales example. Very, very tiny data set. It was about 120 big. I used the deep learning model that was warmed up from the CEI grant project, and then just fine-tuned it on this tiny data set to be able to predict what's the probability that this area is going to have a bad merge. I then applied this trained model to the Eastern Stewart Shelf, where I know from experience, once again, if you're using the ANGD to create a gravity grid, there's going to be issues with the old WMC surveys clashing with modern ones. this is the model output on the right of the deep learning model. And so I'm assuming, I don't think I can actually see the mouse, but on the left-hand side, on the gravity grid, there's a pinpoint anomaly that's dark, where it's clear there's a ground gravity survey that probably needs to be deleted. Model on the right is correctly guessing that. And when we zoom in on some of the other areas where the model's predicting a higher probability of maybe a bad merge going on, and you zoom in on the gravity grid, yeah, you can see some poorly leveled surveys that need to have a look at again. Same with on the right, probably some old surveys from the 60s going down the road. And then also, once again, another survey that needs to have a look at. And I just want to emphasize, this was a very, very quick job, but it really shows that with modern tools, you can start using these powerful computer vision deep learning models with quite tiny data sets. So really, if I can summarize it, you can do anything and everything in Python with open file data with some of the latest research. Just, you have to clean your data, otherwise you're going to get junk predictions. So yeah, thanks for listening to my presentation. If you are at the pre-drilling or target generation stage of the exploration process, reach out to me. I really think these data-driven data science products can really add a lot of value to the existing knowledge-driven process. Or if you have any more questions about this presentation, just reach out to that email address or on LinkedIn. So thank you.
Excellent. Thanks very much, Michael. That's just fascinating. It's one of my big areas that I really, I'm very much an old-fashioned geologist, and I keep thinking I need to learn and understand more. So I really appreciate you taking the time to join us this afternoon. Have we got any questions coming in at the moment? I'm not seeing anything.
We've just got some complimentary comments.
Excellent. Thanks,
Cool.
Helen.
Thanks, guys.
Okay. Well, if anybody has any questions, please send them through, and Michael can type you an answer, or if he can stay for the final session, we'll be able to have a bit more discussion.
I had one quick one if
yes,
there was time.
Rick, yeah.
And sorry, I'm appearing as a timer right now rather than a human being. But I was just interested, in the case of the Northwest Mineral Province work that you did. I sort of missed what data sets you were using, and what your, was there a big data cleanup exercise there, or was it more the choice of training spots that was time consuming?
It was a big data cleanup. So one of the issues is you're using gravity and magnetics to interpret the basement lithology. So you might be inclined to just load up the statewide logging database and then selecting lithologies that occur in downhole drilling in the basement. But the problem is that a lot of those lithologies might not be the ones that are causing the geophysical anomaly. And a lot of the drill holes won't have downhole surveying. So there won't be a magnetic susceptibility. There won't be specific gravity. So you're going to have to go through every single drill hole, manually inspect and figure out from experience which lithology is actually causing the geophysical response. Because otherwise, if you've got a drill hole that's done 800 meters and then it's hit 4 meters of very magnetic banded iron formation, but it's got 700 meters of, metasediment that isn't causing the geophysical anomaly, you need to find those holes and actually ignore all that metasediment, because you can't predict that with the geophysics. You can only predict that banded iron formation. So it's a manual process.
And in the geophysically based sort of, or the process that relies heavily on the geophysical data, how do you take account for the fact that as you suggested, that an identical unit at the surface is going to look completely different in terms of its magnitude and texture to a unit that's at 800 meters depth?
Yeah, so what you do when you're training deep learning models, you can actually randomly alter the input geophysical data while still training it to predict that lithology. So what you end up doing is you start randomly applying different strength, maybe bandpass filters or upward continuations to try and somehow take some of that, let's say at the Mount Isa inlier, some of that exposed basement that may be magnetic, and somehow maybe teach the model, say, this is what it's going to look like down at 500 meters. And you just like do that hundreds of thousands of times while training and progressively make it more robust to different depths.
I'm sitting here nodding, but all you can see of me is 13M00S. So yeah,
I'll nod on
thanks.
you, nod for you.
Yeah.
Excellent. Thanks very much. And still just more compliments coming through, Michael. We'll move on to our next speaker, David Armstrong, who's also a data scientist at GSQ. He's going to focus on Streamlit, turning Python scripts into apps. I'll get it out eventually. Thanks very much, David.
Yeah, and thank you for having me. So I'm going to show how we can take everything that Michael spoke about before and previous talks, the Python code, and make them open access really easily to anybody. So we don't have to install packages and everything. And personally, in my view, this is probably one of the biggest things that's happened in the space in the last couple of years. Python's the most popular scripting language, but previously there was a really big barrier of entry to taking that Python code and then making it available to people. And so there's people who don't want to be installing Python on the computers, packages and everything. And it was really a pretty big hindrance. So this has solved that. So Streamlit, it's just a Python package, and it takes your scripts and it turns them into web apps with minimal code. And so this can be applied to code that are high-end machine learning problems like we had before. Alternatively, if you've got a script that does a useful data transformation, it's only going to take you a couple of lines of code to develop it into an app, and then anybody can run that. So person using the app doesn't have to install anything. They can literally just go to a website and go ahead. And so it's really liberating all that work that kind of happens in the background, stops it being in a black box. So the benefits of Streamlit, simplicity. It just comes, it's another Python package that you install, literally a pip installation. And you don't have to be writing high-end code to use this. So someone like me who writes pretty hacky scripts, even I can turn it into an application. And additionally, this code to turn it into an app is literally often just a couple of words. So you're not writing high-end, you don't have to write custom libraries, custom classes. If you do have those things, you can 100% integrate them, but it's such a low barrier of entry. As I mentioned, you don't have to think about that you're building an app up front. So you might be writing out a script or some code, and then you think, hey, this is pretty useful. It should be an app. To go ahead and turn it into an application, you can just go back and integrate a few components into it without changing too much of your underlying structure. Deploying it is really simple. You can host it locally. Streamlit has a free server which you can deploy it on. You can integrate straight into your GitHub account. And so there are equivalents out there. So in R, there's Shiny, Python, you did have Flask. Personally, I found there was much higher barrier of entry, and you probably did have to have some greater technical skill to go ahead and turn these into applications. So I think Streamlit just really lowers that barrier. So I'm going to try something very silly now. I'm going to try a live demo. So hopefully we can see VS Code here. Thank you, Kate. So I'll zoom in there. I've got some code here, and I've got a mood responder. So I'm going to input if I'm feeling happy or sad, and I just want the script to return a message for me. So this is a very basic structure, but something we do often with Python. You have an input, more often than not, in our case, probably some kind of data. Based on that kind of data, we do something to it and we produce an output. So if I just run it here, I get my message because I'm happy, that's good to hear. If I change it to sad, returns a different message. So script works happily. If anybody was interested in my mood responder script and using it, they would have to go ahead, have Python, open up a terminal or a notebook, run it, and store the packages. So I'm going to show how we can turn this into an application with just 3 lines of code. So the first thing I will do, I'll just scroll down. I'm going to import the Streamlit package, and I'm going to give it a title. And then to run the app, you just go Streamlit, run Streamlit example. So when you're developing, you can host all of this locally. And then when it comes to deployment, you can, as I said, deploy on the Streamlit servers themselves, or you can host it on an instance somewhere, and you'll get a network address. We'll boot this up and we'll get a local address. I have slowed down my computer drastically in the last couple of days. So normally it doesn't take this long. I've just been running a few different things. I'll show this recording and get myself a new computer. So if we come here over into our browser and go into our local host, this will kick up. And there's our first app. Now, you can also see your app as you go ahead and develop. So I'm going to create an input for the user to type in how they're feeling today. So as we can see here, we call Streamlit, and they've got a pre-made widget text input. So I can type now in here how I'm feeling. Now, I haven't actually called any response here, so I'm just going to say if current mood, and so that means somebody has put an input in. We can see I've got an indentation error that appears directly within my application. I'm going to say we're going to write out our response. So happy, and we get that message. That's great to hear. So within 3 lines of code, we've taken that script and developed it into an application. It doesn't matter the complexity of the code. To build the app, it's pretty much the same things over and over. So my response before could have been 100 lines, but I could still just write out the same 3 lines of code to build an app. Just to show some of the other components that are pre-built with Streamlit, we have something such as a slider. I might just zoom into my app here. So this is a dynamic user input. So out of 100, how happy am I? I'm very happy today. And then what I'm going to do is just a few extra things. I'm going to create a dynamic graph based on my user input there. So I'm just going to import a couple of packages, create a graph. Run that. And so you'll see here from on the x-axis, if I move my slider, the x-axis should update. So very simply, we've built a dynamic app that anybody can access. In fact, if anybody went to this network URL here, you should maybe be able to access the app itself. So it's completely open source. So I thought for this presentation, that was just my backup in case my live demo didn't work. Yesterday, I thought for this talk, I would build us a tool-time Streamlit application. And I taken 2 packages or 2 talks previously. So we had a tool-time talk session number 1 last year. We had Morgan Williams from CSIRO, and he introduced us to his Python Pyrolite package, which was made for geochemistry analysis. And then we had Kate introduce us to the GSQ API. So I've combined these 2 and developed a Streamlit application out of it. And so just a disclaimer, this talk is on Streamlit and not geochemistry. So when I show some incorrect geochemistry here, please, any geochemists, don't at me too much. I'm hoping we can all see that okay. So here's my web app. I'm going to select a surface sample I'm interested in, rock chips. And then using the GSQ Open Data Portal API, we can enter a bounding box and we can extract some geochemistry data blocks from there. So if I go extract data, now this is using the API to extract all the geochemistry data sets we have in there. looking for rock chip samples, and it should produce a data frame for me. Just take a few seconds to run. So we can just see on a map here, this is where all the samples I found were located, and they happily live within our bounding box area. Here's the data frame that we extracted. And so then based on that data frame, I'm going to use Morgan's Pyrolite Python package. And so he had a whole range of visualizations that you can do for analyzing geochemistry data. These are the elements that I found within the data frame. I'm just going to pick a couple of random ones to produce a ternary plot. I know I should have checked before if this was technically correct. I'm sure it's not, but we'll see a nice image anyways. And this was just calling a custom class within Morgan's package. And here's just another one we can do. Again, we can change the inputs. Go ahead, select. Reproduce our heat scatter plots. And we call that class and produce all these graphs as well. So, and I only developed that yesterday, so very short amount of time, we're able to kind of make everything open access that we've talked about before. So nobody has to install custom software for this. It's literally just a web address you go to and deploy it. And yeah, I really think it's a big step in kind of liberating data analytics and data science. If you go to the Streamlit webpage, whole range of documentation, but in their gallery, some really cool examples as well. If anybody was interested in using satellite imagery to produce time lapse, I would recommend looking up the Leaf Map Streamlit app. Very cool. But there's a whole range here from vision to natural language processing, and they're good examples. And that's it. So thank you very much.
Thanks very much, David. That's excellent. That's a really interesting example, and great for someone like me to see, because I'm not a Python user at all, and I'm sure there are others in the audience. There's certainly a discussion going. You can have a look at on the chat. Pavel from Saro was talking about their use in the mineral resources group, but also mentioned Dash as another package that does a similar thing. So perhaps if everybody's still around at the final discussion, we can hear a bit more about that. But that was, I really enjoyed your example of pulling together the Pyrolite and and showing it live to us today.
Thank you.
Okay. Yes. Sorry.
Oh, no, just thank you.
Oh, sorry. Okay. And we'll move on to our next speaker, Winping Jiang from Geoscience Australia is going to present today on transdimensional Monte Carlo code for 1D inversion of the audio frequency MT data. Thanks very much for joining us today, Winping.
Thank you, Karen. I just share my screen.
Okay, we're still just seeing the black screen. Ah, there we go. Excellent. That looks good.
Yeah. Okay. Thank you for the invite. And I'm going to talk about the transdimensional microchurn Monte Carlo code we developed in Geoscience Australia for 1D inversion of audio frequency MT data, or AMT. Just hold on. Yeah. It's just, I can't see my titles. So first, we look at the geophysical data inversion. The inversion process is a reverse process of forward modeling. where we have the observed data and we work backward to find the models that can give rise to the observed data. It's rather challenging because there are more than one possible solution or model. For example, on the right, all these 3-layer models can fit a set of data. The question is, which one could possibly represent the true Earth model? This is a non-uniqueness inverse problem. And there are 2 broad categories of methods to solve the inverse problem: the deterministic methods and the probabilistic methods. A deterministic method is an optimizing process. It tries to find the best model that fits the data depending on initial parameter estimation and regularization constraints. However, it gives limited information on model uncertainty. A probabilistic model instead doesn't settle on one single model, but samples a collection of models, could be millions. So the sampling-based approach is a direct search of the global model space, no regularization needed. And model uncertainty can be quantified using the posterior probability distribution. So this plots showing the concept of the difference of 2 different methods. Oh, I need to point out the downside of a probabilistic methods is computationally more expensive than a deterministic method. So it's only applicable to 1D or 2D with fast modeling program. Here we present a transdimensional Markov chain Monte Carlo code, or often called reversible jump Markov chain Monte Carlo. It's built within a Bayesian framework. The transdimensional aspect means the number of layers in the models is solved for rather than being predetermined, which is appealing for greenfield exploration because we have limited information on the geology. And the model parameterization is driven by data and the prior information or prior beliefs of models. It's naturally parsimonious by adapting the minimum structure philosophy, which means models with less number of layers are more likely to be accepted. And the code is parallelized using MPI. So you could run multiple Markov chains with each sampling millions models. Here shows the inversion program workflow. I don't think I have time to go through each steps. I will talk you through later on when I'm showing an animation of the sampling progress. The code is written in C++ at Geoscience Australia. It can be compiled to within a Linux operating system or Windows. It's built on an open source reverse jump Markov chain Monte Carlo library on iEarth, developed at Research School of Earth Sciences at ANU. We have made the code available on GitHub repository, as well as the compiled executable files. So to run the inversion program, first you need a standard EDI file, which contains empty data normally data blocks, and you need to make sure this EDI file contains impedance tensor or apparent resistivity and phase. That's what we use to run the inversion. Also, we need a control file. Control file specifies some basic parameters. For example, here is an example on the right. There's options block, which specifies some parameters. For example, you'll see there's Born-in samples. That's the number of samples at the beginning of the sampling process, which we don't want them to be added to the collection or ensemble of models, because the model not converged yet. The misfit would be too large. Then also the maximum layers, then the maximum depth depending on the data. For AMT data, they are in a range of 10,000 Hertz to 1 Hertz. So normally can map the electroconductivity to a depth of a few thousand meters, depending on local resistivity. And also you could narrow down the minimum resistivity and maximum resistivity. Then we also, for uncertainty, to quantify uncertainty, we may use credible interval. So there's basic information we need to give the program in a control file, then specify the data, EDI file. To run the program, you could simply just using the executable file, then followed by a control file on a single machine. Or ideally, if you have many survey sites, and if you want a large number of samples to get enough uncertainty information, then you may run multiple CPU cluster computers or multiple core computer. Then it's parallelized using MPI run, specifies the number of CPUs. Then we also have MATLAB code or Python code to visualize the model results. This animation shows the sampling progressing over time. As I mentioned, the Born-in period, that's the models before the misfit reached an acceptable level. So if you look at the bottom left panel, that's data misfit panel here, showing the model converge history. We ran the program with 4 macro chains. Then the red models, they are in Born-in period. Its number of is 10,000 models. So before that, we don't accept these models. Only after Born-in period, the data misfit reached a reasonable level. Then we put the new models, accepted models, into the posterior probability distribution. This is a histogram, 2D histogram, resistivity and depth spin. So there are each time 4 models from 4 macro chains were put into the ensemble. Also, there's change point 1D histogram showing the model layer interface change fall into the depth spin. we look at the final result. This is a real data collected in the East Tennant region. This result showing the model data fit on the left panel, the top two panels, impedance tensor. And we actually used quite a few number of CPUs, I think 128 probably, or 64, can't remember exactly. Then also each sampled a million models. And also this, we have the number of layers in the models. So most possibly for this given data set, the 9 or 10 layer models are more likely. Then on the right, the resistivity depth histogram showing the posterior probability distribution. The warm color showing higher probability. And if for uncertainty, we could use, one measure is to use the credible interval bounded by 10th and 9th percentile. That's the 80% credible interval. So the wider means the higher variability between these models, so higher uncertainty. Then narrower, as we all, as possibly we know, the AMT for electrical conductivity, this technique is more sensitive to conductive material. So that's more certain in low resistivity, high conductive material. And another measure of uncertainty for cover thickness estimates purpose, we use this. This is a full width of half minimum in meters. So that's a spike, which shows a predominantly large number of models has layer interface change in this depth range. So we could estimate from conductive sedimentary basin to highly resistive basement, the conductivity contrast occurred around these depths, and the uncertainty is quantified by the width of the half minimum. So we have applied this method for cover thickness or cover characterization for a number of regional drilling programs. For example, in Southern Thompson, Kupana province, and more recently in East Tennant region. Here shows some example model results at proposed drill sites in the East Tennant region. So from these models, we could estimate the depth to basement, which can help with drill site targeting to reduce uncertainty associated with intersecting targeted stratigraphic units. To a larger scale, we produced cover thickness at 131 surveyed sites. Then we produced a cover mapping. So from the right side, this map, we could say in the southeast grayish region, the cover relatively thinner. That's predominantly Georgina Basin, maybe some part of Taco region, province. Then to the northwest, the cover relatively thicker, but there is a basement high here. So this drill site is located here, and we also got some information from potential field data and seismic data. So we could see there is a basement high here. That's why we put a drill site at this location. So what I'm trying to say is the thicker cover region, which means beneath Georgina Basin, South Nicholson Basin exists in this thicker cover region. So from this cover mapping, we would interpret as South Nicholson Basin is bounded by this fault instead of previously mapped this dark brown boundary. So we could make adjustment because previously mapped based on sparsely distributed borehole, limited borehole data and potential field data, which not very sensitive to depth. So I think I'll leave it here, and we acknowledge the help from ANU, Professor Malcolm and Reese from the Research School of Earth Sciences.
Excellent.
Yeah, I'll leave it here.
Thanks very much, Winping. That's really interesting, and it's good to see the example and the results there from the East Tennant region. I'll definitely have to have a look at those in more detail because it's an area I'm specifically interested in. I'm just trying to check through and see if we have any questions at the moment. Anything coming through in the chat? There's questions from Kate Hine. She's done similar things for AEM data, and it was so good to get an estimate of the level of constrainedness, but it requires a supercomputer. Does the same thing happen for the MT?
For MT, so the constraint level of constraint is, yeah. So for at this stage, we haven't applied any reference model or constraints. And the idea of probabilistic modeling is to sample the whole possible models in the global model space. So yeah, I think I have seen some work done in this space by a PhD student. I think he already finished his PhD so he has done some constraint, applied some prior reference information to these similar methods, and he found the constrained models have more certainty. Yeah, for example, when we quantify uncertainty, for unconstrained model would have higher uncertainty, but for constrained would have lower uncertainty. So does it make sense? Like with constraint, the uncertainty with constraints. So if the prior the geological information accurate, if we apply as constraint to probabilistic modeling, then that would make the result more certain. Yeah,
okay.
At this stage, we haven't applied. So the uncertainty could be larger, but it's quantified. And for good data, simple geology, the uncertainty is low. Yeah, but for more complex geology, we see some examples. Real data we collected. Yeah, more complex or more noisy data, we get higher uncertainty. Yeah,
Okay.
but the good thing is uncertainty is quantified. Yeah, you
Thanks
have
very
good
much.
knowledge, then we can reduce uncertainty.
Excellent.
Yeah.
Thanks very much. I'll perhaps if Kate has any follow-up on that, she can put a comment into the chat, and you two can follow up. Thanks very much again for joining us today. Our next speaker, Kirill, and I apologize if I mispronounce your last name, Kousoubov.
That's pretty accurate.
Okay. Who was previously with Geoscience Australia, as I understand now, but is now a senior software engineer with the World Food Program. He's going to talk to us today about Geo-registered Xarrays with odc-stac and odc-geo in Python. Thanks very much for joining us.
And thank you for the introduction. Is my screen being displayed okay?
Yes, it's displaying properly. Thanks.
All right, excellent. So nothing as complicated as probabilistic uncertainties of all this stuff. I'm just going to talk about some software that Geoscience Australia have worked on for a little while, and I've been taking care of it for the last few years. And maybe some of you are familiar with the Open Data Cube software system that allows to load raster data, geo-registered raster data from network resources, and it maintains its own database and all this stuff. And so if you ignore the hassle of maintaining a database, you get the results pretty quickly like this with a simple Python code. You ask what you want to get, a particular product or longitude, latitude. When you want to, with the time period and stuff, and it generates the Xarray data set, which is a very convenient thing to work with in a notebook. Then, you know, that, why do I keep, sorry. That data looks like this in this particular example, which is a Kangaroo Island on January 9th. So that was all great, the data cube, but it does require significant effort on user part in terms of database management. And in Geoscience Australia, in CSIRO, there are deployments and they are managed and it's fine. But I think we thought that there is a lot of technology in this system that can be used outside of that environment. That can be useful even if you don't have the database that somebody else maintains for you. And so we went about to extract a couple of those into separate libraries. One I'll be mostly talking about today is the first one, the geometry utilities, the odc-geo, that takes out of the data cube library all the interesting bits to do with geometry. Essentially, it's shapely. It is shapely under the hood, but with CRS and with the projection information attached. And it also provides some interesting interfaces, interoperations with Xarray, which I'll show you in a second. odc-stac is another one that was recently taken out as well, kind of. So stack, if you don't know familiar, is a spatial temporal asset catalog. And it's basically a new standard that everybody wants to, that we hope everybody will adopt and start using to describe the data sets that are provided in the cloud in particular. If you're familiar with dealing with metadata, you'll know that this can be, you know, frustrating and hard. Everybody has different formats. Some even have it in binary. So Stack is trying to constrain that a bit. It's using JSON under the hood. It's using GeoJSON under the hood, essentially, which it's a useful standard. And you can, and the important thing here is that you don't need to maintain a database to generate that same sort of data I have shown in the previous slide. if somebody else maintains a stack catalog of the data that they expose online for you. And so, but anyway, let's have a look at the demo first. The demo will be mostly about the geometry classes, which I think are pretty cool, because for the stack, if we have time, we'll have a look because there is already available documentation that describes it pretty fairly well. So these are some URLs. By the way, the size of the font, is it too small? People can see okay? I can make it bigger.
Oh, it's visible. It's okay.
All right then. So I have defined some. I have imported usual things for me: matplotlib, Xarray, NumPy, that sort of stuff. Define some simple functions for displaying things. So the odc-geo gives you a bunch of geometry primitives, essentially, that are defined in the context of a projection, right? So it's not just a geometry like odc-geo, for example, exposes and Shapely. It also has a CRS. Like it's not something complicated. It really is just a geometry plus a CRS object, and we're using well-known, we're using PyProj for CRS, and we're using Shapely for the geometry operations. So let's get some data. So we have from GeoPandas, we have this natural Earth low resolution data set, and we're going to select an Australian polygon out of it, right? And we're just going to convert it to the odc-geo format from GeoPandas over here. So this is really just geometry. This is displayed by Shapely and the CRS. Because you have that, however, you can compute bounding box in a specific projection. You can change the projection of the geometry, right? But you don't have to do it here. You can also change the projection of the geometry in GeoPandas itself. Here, the 2CRS method is that from over GeoPandas. And the extraction will detect the fact that the GeoPandas gave you a geometry with a Australian Albus projection rather than the original projection, which was PSG 4326, right? So the geometry defines a number of various methods you might expect. For example, a boundary gets you a polygon, gets you an exterior of a polygon, essentially. We can then transform it through some function. In this case, we shift the Australia by 500 kilometers, one of the ways. And then we can perform operations like unions in this case. So the majority of set operations supported, everything that Shapely supports, we support. The only thing, we insist that the geometries that we're operating on are defined in the same projection. Same stuff, you can rotate it by an arbitrary affine matrix. You can find the bounding box, expand it by 100 kilometers, and then subtract the Australia out of it. But if you try to do any of that on geometries defined in different projections, here we're projecting Australia into Web Mercator and then subtracting the Australia in Albers, we get a CRS mismatch error, right? So this is very useful when you're writing a more complex data processing software to keep track of what is going on. Okay, so this is just the geometries, and a lot of that's already available in the GeoPandas great package. But this one, while GeoPandas is focusing on arrays, we operate on a single one. But what's important, what the thing that ties it all back into the rasters is this thing called GeoBox that we call GeoBox. So GeoBox is essentially this. Okay, so GeoBox is a mapping essentially. It's describing an image plane, right, for which for every pixel, you know where it's located on Earth. All right, and you know that because there is a linear mapping. There you go. Let's just move this up a bit. There is linear mapping. Sorry. Live demo is always a little bit frustrating. So first we created the geobox. Yeah, okay, so sorry, I skipped some steps. But we don't, like we're saying, okay, fine, this is great. This image essentially would fit this geometry, but we want to add some padding, and then we also need to round the width and height to some reasonable number. And so we still end up with the geobox. All right, so the geobox, now this should work. It's basic, well, it has a, as we have seen in the image, we can tell where it's located on Earth. That's a geometry, a polygon, where its bounding boxes is. But the way it's defined, what the things that are actually like make it run, is this three things really. The projection which it is defined, the shape of an image that it describes, and the linear mapping, these 6 parameters over here, from the pixel space to the projection space, right? And this is a typical shape, a typical format that is used, which is the square pixels, this is the essentially a resolution of an image with the y-axis flipped because this minus, and then it's all translated, right? So if you take a pixel 0, 0, that you multiply by 5,000 is 0, and then that's where it's located in x coordinate of the projection space. So what can you do with this? Well, what you can do is you can build Xarrays, data arrays that contain the information within them that describes the projection that is involved. So how this works, we are storing a CRS on an Xarray. We're storing, we have the coordinates for it. And what that enables us to do is to save it to a file and then load it back. And we still have the same information present. Similarly, we're offering options also to do, this is with third-party 2 dataset, just calls the netcdf library internally. But because of the way we have constructed this Xarray following netcdf CF conventions, simply saving it with the 2 dataset metadata, with the 2 dataset method provided by Xarray, also writes the georeferencing information. To verify that actually happened, you can read through the GDAL info on this stuff. But obviously, this is 0, 0 is not very interesting. We can also do more complex things, like, for example, rasterizing the geometry into geobox that we want. In this case, we want a 4 times smaller geobox than we displayed before. And yep, that's it. That's what we got. We also produce the simple resampling methods that you can change the projection of this thing, and it all figures out where that really is. And you can slice through it. You can pad, zoom out, and all these other things that you can just play around with with tab completion and things like that. And I think I'm out of time, so I'm gonna go back to this thing and just say that while we've done a lot of stuff on top of it that I think is very useful and user-friendly, it's all actually driven primarily by those libraries displayed here. And there are some links. Any questions?
Sorry, I was having trouble getting my mouse back to the right spot to turn my microphone back on. Thanks very much, Kirill. That was excellent. I'm just looking through now to see if we've got any quick questions. Please post them through quickly. Otherwise, we have just one more presenter before our final discussion session. Excellent. Just some good comments coming through there. Thanks again. And our final speaker is another recording, Vincent Dinh, on another QGIS topic, focused this time on raster processing and geological mapping with ASTER. And thanks very much to Vincent.
Hi everyone, my name is Vincent Dinh. I'm a GIS specialist at GIS Pro, a company providing GIS services in mining and exploration. Today, we'll show you how to process ASTER data with QGIS for geological mapping. So this presentation is part of a broader training called QGIS for mining and exploration, initially developed by a geologist called Grant Boxer, that we now do in collaboration with our colleague John Bryant from Mammoth Geospatial. Before we start, I'd like to say a few words about QGIS and how relevant it is in mining and exploration today. So QGIS is a major open source GIS package that comes out of the box with tools and algorithms that make a range of GIS analysis available. So typically QGIS can help during several phases of exploration, from planning future samplings and drill hole programs to collecting data on the field, analyzing geochem data, visualizing drill holes and creating cross sections, processing rasters, and of course, creating maps. So from our experience, since a couple of years, we are seeing a steady growth in mining companies adopting QGIS, to the point that it's creating a positive feedback loop where companies start creating and sharing dedicated geological plugin to extend QGIS functionalities and improve specific workflows. So learning QGIS now is certainly worthwhile. But in the rest of the video, we're going to demonstrate QGIS raster capabilities and how to process ASTER data for geological mapping. So let's start with presenting ASTER. So ASTER is a remote sensing instrument, part of the Terra satellite, launched in 1999. It can take high-space spectral images in 14 bands, with a resolution varying between 15 meters to 90 meters. So ASTER imagery has proven to be well suited for identifying minerals and revealing geological features on the ground. So ASTER data is freely available worldwide, but note that the SWIR sensor, which includes a band 4 to 9, became inoperable in April 2008, and therefore only data acquired before the date will be suitable for mineral mapping. So there are quite a lot of resources regarding processing ASTER data for geological application. And one worth mentioning is the ASTER Mineral Index Processing Manual, compiled by Alex Kalinowski and Simon Oliver. So you will be able to easily find it on the web. And it does a great job at listing the bands and band ratios that work well to identify specific mineral formations. So let's see how we can apply this knowledge and process ASTER bands in QGIS. So the example I'm going to show you is located in northwestern Australia, and we'll try to create an image that discriminates well between different types of geology. So we will use this formula here below, and basically the formula means that we will create a composite RGB image, and each channel, red, green, and blue, will contain those band ratios. So in the red channel, we'll have band 4 divided by band 7. In the green channel, we'll have band 4 divided by band 3. And in the blue channel, we'll have band 2 divided by band 1. Okay, so let's see how we can do this in QGIS. Our first step will be to download an ASTER image over the area of interest. So to do that, we'll use a QGIS plugin called the Semi-Automatic Classification plugin that's available via the plugin manager. And the main reason to use this plugin is that it allows us to download images directly from QGIS. So it's pretty convenient. So once installed and enabled, we'll click on the plugin icon and go to the download section. The only prerequisite before searching and downloading ASTER data is to register to the NASA Earth Data Portal and configure the plugin with your username and password. Once done, we can head to the search. So first we have to set our search parameters. Under product, we'll select ASTER level 1. Then we can select the date range, and we'll need to look for images taken before April 2008. Finally, we can define the search extent by clicking on the red cross and drawing an extent in QGIS. So we are now ready to click on search and see what comes up. So we have few results here, and I'm only going to keep one image and remove the rest. And once done, we can click run, which should download the image. So we'll skip this step and directly go to the downloaded image. The ASTER image is just a single HDF file, and let's add it in and select the band we need. So you'll notice that the band number is at the end of the item name. So let's select band 4, 7, 1, 2, and 3. So when the bands come up, you will see that the projection is undefined. So we'll fix that, and we might also change the layer name just to make it clearer. So I'll change the projection to WGS 84 for all of the images. So now we're ready to do our band ratios. We will use the raster calculator under the raster menu. So we can select our bands in the raster band panel, and we will construct our expression in the raster calculator expression window. So our first band ratio is the band 4 divided by band 7. So once we have the expression written, we will specify the location where to save the file. And then we have to repeat the same operations for the two other bands ratios, which are band 4 by band 3, and the last one, which is band 2 divided by band 1. So now the last step, when all the band ratios are created, we will be able to create a composite image. An easy way to do that is using the Build Virtual Raster, where we can select the layers to merge into an RGB image. So the order of the layers in the input panel define which band will go into the red, green, and blue channels. We have to make sure we click the options place each input into a separate band before running the process. So here is the result. We have a nice color composite made of our band ratios, and we can enhance the color using the raster toolbar and play with the settings to have a better visual. Here is an example which shows nicely the different ground mineral units. So this concludes this demo on using ASTER for geological mapping. I hope you enjoyed it and that you will give it a go. Thank you.
That was excellent. Thanks very much for Vincent for taking the time to provide the presentation to us, but unfortunately hasn't been able to join us this afternoon. So traditionally now, Helen, I might hand over to you to thank all our speakers and let everybody know about the next steps. But I will start going through and promoting anybody who wants to stay is welcome to come along and join us as a panelist for the final discussion.
Absolutely. I also know that Rick needs to leave us very soon as well. So normally what we do now is we invite all of our audience to participate. And so you'll have noticed that you can't turn cameras on and that sort of thing. But Karen will promote you to be a panelist, and then you'll be able to turn your cameras on, unmute yourself and start talking and asking questions, telling the speakers what you thought of their work, providing stories about similar experiences, data, where you might want to apply some of these fabulous tools. So please participate. We always have that awkward couple of minutes while nobody wants to talk and we have to pick on someone and make them talk and that kind of thing. So that's okay. Once we get started, it's very difficult to get everyone to stop. So grab a drink if you want to and join the conversation.
I have a question for the assembled group before I have to run off at just before 5. So thanks everyone. Those are great talks. I'm interested to know if anybody knows of a geophysical processing module for QGIS. So something that does the basic stuff that say Discover would do in MapInfo, or that not the high level Geosoft stuff, but just derivatives and reduction to the pole and so on for tilt algorithms and so on for QGIS. Does anyone know of anything that does that, or any sort of plugin that does that in QGIS?
There are crickets.
One comment, Ian Anderson saying no.
Yeah. Well, I don't have the time, or other than lacking the time or ability, I'm ready to do it myself.
Alex is saying there's an archaeological toolbox that offered some functions, but not the higher level stuff. Do we have any geophysicists on the line that might have played around? I know if we had some of the GSQ geophysicists, they've definitely used QGIS, but they're tied up with meetings at Geoscience Australia, I think, unless they're on the way home. No answer.
I had a question for David too. How complicated? You showed some really good simple examples of conversion of just a Python script into something online. How complicated a script have you managed to implement in the same way? Is there any limitation there, or?
No, I haven't been able to find a limitation. We ran a concurrent ore body clustering program on it, which I think was in the background. I think it runs 40 different machine learning kind of applications in a pipeline, and I've got that up and running, and you just click one button and it runs it. So haven't come across any limitations, and biggest one might be computational stuff, but you can host that on your own EC2 instance and stuff. So it shouldn't be any dramas.
You come up with some big things if you want to give it a shot, David.
So what was that? I missed that.
come up with some large things if you want to give it a shot. There's actually a Geoscience Australia 10 gigabyte Northwest Queensland inversion you could start playing with. That's maybe like 100 million cells or something. So,
yeah,
there you go.
Really, the biggest challenge was just printing out kind of the terminal messages on, so people could kind of see it was still running as opposed to a spinning wheel and then some balloons at the end. So it didn't want to make a complete sandbox, but yeah, we'll give it a test. Really interesting one was Leaf Map, which is a mapping service that was kind of built for Jupyter notebooks, and they've taken and run it, and they do amazing things with satellite imagery and stuff. And anybody can create time lapses using satellite imagery, and it's been really interesting following on LinkedIn people around the world creating their time lapses for whatever regions they're all over the world, and just kind of seeing that growth and stuff. And yeah, it's really opened it up.
Well, everybody's being shy this afternoon. Hardly anybody's accepting the invitation to be promoted to a panelist.
Yeah, I just went through the same thing. I'm finding the same thing.
Yeah.
Wimps.
Little buggers. Yeah. I'm going to call out Clive Foss and James Jensen for being the brave audience members.
And Richard Scott.
Oh, and Richard, of course.
Yeah.
You're just there. You're just, part of our audience. It's awesome.
What did you think?
You have to go.
Thanks, Rick.
What was your favorite tool from today, Richard?
Well, Richard's actually recommended a few of these. He really helped out when we started a discussion with Tool Time 1, and he gave me a lot of recommendations. So he's been very helpful with this and very involved.
I'm definitely a fan of Kirill's work, for one.
Cool.
As well as Michael's, but most recently, I think I was using odc-geo last weekend. So
awesome. That's good.
Helen, it's Evan here. I guess from my perspective, Tool Time 1, from what I've heard, was really good, and I think this afternoon has been quite interesting as well. What are people interested in listening and learning more about, I guess, when we run Tool Time 3? Is this something that we haven't covered off, or where should we go to next? I guess we're all ears.
Oh.
Well, Alex has got in the chat Oasis montage. We haven't talked about that one before, have we?
I think that was specifically about the geophysical processing that Rick had raised. So, yeah.
Yes, Richard.
Some of that domain about the I guess QGIS plugins in the Fatiando family of libraries. There's requests for doing Fourier-based Fourier-based sort of stuff. So people will be able to take that code and make a plugin out of it. So I can point people at that and say, interested.
That was going to be my response to it, is just take that library and put it in Python and QGIS.
Oh, look, a few people have felt guilty and they're accepting their invitations now.
Well, either that or they've just gone quiet and they haven't noticed me pinging them again.
Oh, excellent.
I'm just having one more go for anybody who's still there.
So Michael, if you could create more tools and add to what we've already got, what would you do?
Create tools for what?
Oh, well, what would be the problem that you would want to solve?
Well, while he thinks about it, I've got one. Speaking of commercial software, there was a grid merge program that started at Geoscience Australia. So I guess, taxpayer funded and whatever. So presumably there's code exists for that somewhere at the start, and then that turned into a commercial product. So I'd like to know what happened to the work that's in the interim that we all pay for.
We can follow that up.
Grid merge that all the geophysicists use and pay however many thousands of dollars a year for the privilege. So it's a tool I like a really good open source grid merge program. So,
yeah. Yep. We can follow that one up.
Yeah, because there's not many, I'm not seeing many Geoscience Australia names there on the list today, so everybody must be busy, but
well,
that's definitely Winping. I don't know if you know anything about that topic.
I don't really
Intrepid,
know
that's the one,
about
that's
this topic.
Yeah.
Yeah, we have we have IT supports for tools development if we can make a business case, which we made some, but I haven't heard we develop anything to go commercial.
This was a while back. This was
you said it was called Intrepid, Richard, did you?
Yeah, Intrepid is what the geophysicists use for this stuff. Yeah.
I thought they are a commercial company.
Yeah, they
sometimes
are. If you
pay them to do some work.
Yeah, if you read the Bryant Minty papers or whatever about the development of this stuff, there was like work done with Geoscience Australia. So I'd like to know what the story is.
Yeah, they did some work for us. Like we contracted them to do some work. Intrepid. Yeah, they even did some work recently for the MT metadata standard. Yeah, and also not many Geoscience Australia colleagues here was because we had a division brief this afternoon. From 2 to 3, and from 3 to 4, the ACT branch of ASEG, the annual general meeting. Was on from 3 to 4.
That the last Thursday of every month is GSQ UQ webinar day.
Also ASEG, ACT branch seminar or meeting on this day, and the dinner tonight at 7.
Well, that's fun.
AGM.
We still had well over 80 people attending. I think that's a good number, and we do record our sessions, so everyone in Canberra can visit the webinars later.
Yes.
Leslie has joined us. Leslie, give us the spiel.
I was multitasking this afternoon. I've had some urgent stuff, which is why. Anyway, okay, yeah. So you're going back ages with that grid merge code, and this was before we had open source software and blah 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 blah. And so what had been developed was, what can I say? What's the polite word? Given over to Intrepid, and then they commercialized grid merge. So again, this all happened in the period before open source. So I'm not too sure exactly what you can do about it, because whoever raised the issue, started at BHP, yeah, that's right. So it's come up before. Sorry, I left GA in 2014, so it's been around for a while. But the whole issue started pre-open source software, and it's hard to go back retrospectively to whoever suggested it. And so the other thing I'd like to do is Winping, I don't think Kate was asking a really specific question about the work you were presenting. Yeah. You are doing that on the NCI supercomputer, are you? Or
Actually, I sent a message only to panels, not to everyone. I did answer this question. For large number of survey sites, we often run NCI using multiple micro-chain to sample millions models. Actually, the example I showed was run on NCI. And for small number of sites, for example, in Southern Thompson, we only surveyed 10 sites. Then just for drill site targeting purpose, we could just run on our computer for a few sites. For 131 sites, I did run on NCI. Sorry, I didn't send to everyone. I only sent to panel. Yeah.
So to those of you that are here, and I don't want to get into it, I just wanted to say that AusScope and NCI are collaborating on a project that I've just put in the chat for you all. It's called 2030 Geophysics. And this is the problem that some of the geological surveys or overseas institutions have access to HPC. And the advantage of it is that you can do much larger inversions and at much higher resolution, and you can do probabilistic modeling. So basically that project that I've got funded with Hope is aimed at working out, my God, if this is what we're going to do, what can we do with the data? So if you go back, when you get onto the supercomputer, then you can actually use your data at higher resolution and in rawer forms. And so we've got this chicken and egg situation of trying to work out, oh my God, how do we make the data so it works in this versus people wanting to test and try it. And recently, Geoscience Australia has its own partnership with NCI, so it does that. But there's a lot of people that don't. And AusScope is setting up an offer for projects that want to build a HPC infrastructure, and it's been open to some of the states. So it's open to the state surveys as well, because they're all members in AusScope. And so anyway, look, that's just a heads up on what's going on. But if people want to try or experiment, then that's informative to me running that 2030 Geophys project, because we really like your current data formats and how you're accessing them just aren't going to cut the mustard in this high performance environment. We've got to think more about machine readability of the data, et cetera, and getting away from file downloads. So one of the things we're doing is moving some of the national geophysical data sets, Geo is part of this, into the high performance environment. So anyway, that's not what this session is about, but, and there's Pavel, so he's got something to say, because we're doing it in collaboration also with CSIRO and the AVRE, the AusScope Virtual Research Environments Project.
Actually, more of a question, Leslie, just looking at this 2030 geophysics collection, what relation does it have to the good old GADS server? You're muted, Leslie.
Oh, I thought I was just trying to save people the tragedy of listening to me. Okay, so the base data in GADS, if you go into GADS, is actually a lot of, like, you know how you can get the grids out of GADS, or you can get the the individual surveys. In NCI, we actually have the gravity and airborne magnetics there as and radiometrics as point data sets. So we've turned them into point clouds, or sorry, Geoscience Australia did that.
Mm-hmm.
And now we're working through the MT data, and rather than people having to deal with the EDI files or the what's the other one, the models, you can go back to the original level 1, level 2 data and start to really work that data up to the way you want with your parameters and et cetera. Now, it's turning out to be a nightmare because I think, as you all know, there haven't been standards for collecting MT data that everyone's agreed to, or a standard has just come out, developed by the USGS and IRIS a couple of months ago, and we're now trying to work out, we're having a meeting with them to work out how to get the historical MT data into this MTH5 format, because that's what you're going to need in order to be able to use HPC. And when I say the data, I'm working with AusScope, so it's the AusScope funded AusLAMP data, which is Musgraves, South Australia and Tasmania, I think.
Leslie, are you seeing you're going to work with USGS for the legacy MT data, mainly AusLAMP data? into MTH5 format?
We're just trying to ask them, and again, I'm only touching I only got the funding to do OzScope data, so we're just trying out with the Musgraves data set. And so we're just having a meeting next week with them to try and work out how we're going to do it.
Actually, we already started to do that for our only collected by Geoscience Australia, all LAMP data. We package into MTH5 format. We started only just recently. Yeah, it's going well.
Yeah, we need to
package some data already.
Yeah, we need to catch up with that, and because as I said, the project's only kind of just got going, and it's really chicken and egg stuff. What do you do first? And we're also looking at passive seismic and DAS seismic data. But anyway, that's just another world that's starting to form based on that project.
That's good to know. Thank you, Leslie.
Thanks, Leslie.
Sorry, don't expect miracles either. It's a research project.
Got to start somewhere.
Well, the big problem.
Geoscience, we just make it up, don't we?
No, the big problem, as you all know, is the data collected around 2014, say 2016, where it's all handwritten in paper logs. That's the real problem we've got.
Yep. It is, but a lot of companies have digitized that data. So you could work with them and see if they'll donate their databases of historical data.
Well, I think the eye-opening thing is, as Winping showed us today by using the supercomputer, what you can actually do. And I'm going to be blunt, there's a real point in time where we no longer have the gift to be able to retrieve some of the earlier data sets, because the raw data as collected hasn't been what's been made available. It's more the products and the models and the images. And because it hasn't been brought online, it hasn't been looked after. Or that's really bad. I don't mean to say that, but you know what I mean. It's not as accessible. When people try to go and get it, they suddenly realize that if they can't find the person who collected the data, they can't do much with it.
Yeah.
It's true.
Yeah. So Michael, what about your work, the machine learning work you're doing? Is that just you're running that on a computer at home?
Yeah, run it, but
well, at home at the office.
Yeah. Yep. But my work PC is pretty high end, I guess, in terms of you're doing a lot of graphics card processing, which might be a bit different from performance classes. But it's probably still pretty small scale compared to maybe the deep learning research that's done at the big tech companies, because they're working with data sets that are like probably into the billions size now, where it costs like $100,000 worth of computing to train a model. Thankfully, we're not at that stage yet, so I can still do it on the work PC, but I don't think so far I haven't encountered the need for deep learning style models to actually need like really powerful computers, unless you're just being impatient and you want to run like 100 different models at once. Otherwise, you can still run
parameter tuning.
Yeah, that's the big issue. That's the latest project I did on the collaborative exploration initiative. Those self-supervised deep learning models, although they enable you to then take that model and train it on a small data set, and that only takes like 1 minute or 5 minutes. The self-supervised model itself takes anywhere between 10 hours to 24 hours. And there's probably 20 or 25 different settings you can tweak to optimize that. So you can imagine there's hundreds of thousands of different possible combinations to search for the best optimized model.
Okay.
And that's where having an access to like 1,000 graphics cards would help a lot. But that's any deep learning project has this problem where there's probably a different setting that will provide better results, but you don't have infinite resources, so you kind of have to make a guess of what's good enough.
But as I understand from what you were saying, so if you took, a chunk of the Mount Isa region and did that initial step, the
self-supervised,
that then just sits there and you can then use it for a number of different detailed studies.
Yeah, and that was the kind of what I was getting at with that little model that was just checking the quality of a grid merge for gravity data, is that you got like an off-the-shelf deep learning model that you can then say, okay, what question can I answer using gravity and magnetics? So that's a real time saver, because those tiny models themselves also have a lot of different settings that you need to optimize for. So if you're using the self-supervised process, you can churn through a lot more settings if your model's only taking 1 minute to train this time rather than another 10 hours or 5 hours. So yeah, there is lots of efficiency gains using these pre-trained models. And that's, I had to cut out a lot of what I wanted to say, but what's driven a huge amount of innovation in modern tech companies and modern deep learning is, especially in terms of computer vision, where you're predicting, what's inside this image, is you have these huge pre-trained deep learning models, and they've been trained on this data set called ImageNet, which is like 11 million images of the internet, basically. And so lots of people just take a pre-trained ImageNet model and then fine-tune it for their little their startup or their little thing, like maybe they want to predict dogs versus cats from the security camera. And that's kind of what I developed with those self-supervised models, is kind of getting into that same space where you already got a big model and then you can just fine-tune it on a tiny problem.
Yeah, that's very reminiscent of what we're doing with GeoClerk, right? Like it's taking those initial training sets of here's all the images and refining it down to understand the geologically relevant ones. I do wonder with those, is there a way to kind of do it for geophysics? And, or is that what you're really kind of leaning towards, is that you're building these kind of base trained sets for understanding seismic or magnetics, and then people can go and look for different anomaly types? Or
yeah, that's pretty much it. And it's been a bit tricky. Just the research for these self-supervised models has always been targeted towards computer vision. And so the techniques they use to train these models have no applicability to geophysical data. So you need to figure out how to take that research and then it's like, how do I translate that into, potential field magnetic gravity data? There's applications in seismic too.
Cool.
Sounds like there's a lot still going on, and we will definitely need a tool time 3 next year for everything that's happened between now and then.
Yeah, we need everybody to send in some suggestions, so we've got a running list to work on and line things up for the next time.
Why do we have to wait a year?
Because we've got so much else to talk about, Leslie. Like there's when Rick and I sit down and come up with the topics, we usually come up with about 2 years worth of talks that we could, or sessions that we could do. And then we've got to cull some out and go, oh, well, let's just have our top 10 in the year. And then, so.
No, can't you sneak it in as a Christmas present?
You should be busy doing a 200-meter gravity inversion of Australia for us.
Exactly.
Hang on, young man. I'm a geochemist.
That doesn't matter.
I just understand how to structure data. I'm not a geophysical programmer.
I can do them.
I used to be a geologist. I don't think I'm even
still
that
are.
anymore.
Yeah, one thing that I thought that was really cool, Karen, at the Aegis conference was that digital twin that Stephen was doing. Is that like a known thing? Is that something you can showcase? Because that was pretty cool.
It sure is.
Yes,
Yeah.
yes. You know, the first iteration is due for release in June. So it's, you know, the project's been a collaboration between UQ and GSQ to get focused on Northwest Queensland to get that large range of data sets in. So that will be ready for release.
Yeah.
And that will be web-based. So for the others who aren't familiar, this is, we're working with Euclidean to be able to deliver and visualize in 3D a large range of data sets from, you know, from seismic, SEG-Y, and all the AEM data sets across Australia, and then to zoom in down to look at a drill hole and look at the photos of the drill hole and even thin sections or
And
details.
then TEMA, and yeah, so it's
TEMA,
infinitely scalable.
Yeah. And so it's about the way in which the data is stored so that you can seamlessly zoom from, you know, from all of Mount Isa down to a single drill hole or a single TEMA image. And I don't know for anybody who's looked at, tried to view the AEM data on Geoscience Australia's 3D visualization package and select, it struggles. And whereas this, we've got not all of it, but a good chunk of it loaded in, and you can just zoom in and out and visualize it. And, you know, some of the more detailed AEM studies in the Mount Isa region. So we'll have to highlight that shortly.
Well, that's actually going to be presented at the GSQ workshop in Townsville, which will be a hybrid face-to-face online event for those who can make it to Townsville. That'll be the 25th and 26th of June, and we will have 25th, 28th and 29th. Oh my God, thank you, Evan. And we are working to get some comms out about that very soon so that people can put it in their diaries.
Excellent. Oh, thanks. David's put in a link on with Steve just giving a quick overview.
Oh, thank you.
Yeah, yeah. Excellent.
Wow, all right. Well, it's nearly 5:30. Hang on, Leslie's decided she's not talking to us anymore. She's just going to put things in the chat. Is that right?
All right, unmute. Sorry, I sent the 2030 project brief to the panelists. I didn't know whether you could see it.
Oh, to everyone. Okay.
I just resent it to everyone, and someone said maybe we'll use the cloud, and I'm saying I don't know what you'll be using. You'll be at exascale, but who knows whether it'll be, you know, big HPC or a cloud because it keeps moving around. But what we're looking at is the challenge that one of the reasons why HPC is not widely used in geophysics at the moment is because the data is not in formats that it can be consumed by them. So we're kind of looking at issues we know people are having and then saying, well, hang on, if you're going to go to exascale, what else? But it's not as if we're acting blind because the climate community is already playing in this space and asking these questions. So, and for crying out loud, time series data is time series data, whether it's geophysics or what. So, yeah. Anyway, that's kind of, we've just got some funding from the Australian Research Data Commons to explore this. Because those of you who saw the National Research Infrastructure Roadmap, it talks about high resolution data, it talks about exascale. So this is kind of one of the projects that got funded to ask these questions.
Kate is saying it would be great to have that as without a serverless.
Yeah, again, that's the option. Like we got in a lot of trouble with our last projects because people kept saying, oh, that's not what our clients want. Our clients want images. They want to download it. They want to play with it locally. So in this one, we're saying, hey, guys, we're 10 years out, okay? We're not trying to solve today's problems. We're saying, if you're going to have this much, what do you do? And there was a similar project funded by the European Union, of all things, called CHEES, Centre for Excellence in Exascale Computing, and that focused on the software. And that asked questions about what do we need to do for software for, say, tsunami or volcanic modelling. It was very hazards-based to be able to do what they call faster than real-time computing. And so this is just another one that's going on for data. Yeah, and that's the other thing too. HPC is massive in the oil, but it just has not taken off in minerals, and I don't see why not.
Leslie, it also makes me laugh when people, our users, potentially want to either download stuff or upload stuff. We're actually now trying to push our users, our clients, to access data sets online as much as possible. Yeah. If something is available through the API, that's the way to go. And it looks like there is a trend that more and more organizations are actually moving towards both exposing their APIs or the data through APIs, and also using APIs to retrieve data rather than copying stuff.
Yeah, sorry.
What are your thoughts on that, Richard? From a company, perspective where
one of my machine learning model ensembles is 10 terabytes, put it that way.
Yeah.
So you can't really download those. So you got to do something else.
Yeah.
APIs only go so far, but like the cloud storage, I guess, is next step. Where formats that are that are good for cloud access, and are just sitting on S3 bucket or Google Drive version of this 3 bucket, and then that access to it scales really good, but it's static data. Your API then just describes your links. Like that's what STAC is. It's a special temporal asset catalog. It just returns a bunch of links to files that you can grab from Amazon, Google, or Microsoft directly without running your own service. But you pay so much for traffic. It's a challenge for organization to share data like that.
So yeah, it's if you're hosting it locally for the API, so if you have your own data center and you just you don't have the egress costs, then through the API makes a whole lot of sense. But yeah, when you're talking about large data sets as Richard is, or geophysical data and piping that to everyone, you almost are better off just printing a hard drive and sending it out, because multi-terabyte data sets multiple times a day it just racks up in huge costs for the cloud providers.
Yeah, big RAM to fill that up, you'll spend a lot of money.
With huge data sets, it might be also worthwhile just to deploy your compute node or whatever you want to do with the data into the same region, and just to run that computation on the large data set and get results back. So you can go the other way around. Yes, it all depends on the data set and the size of it. But yeah, it's all, I guess.
Yeah. As long as you got models that can deploy into AWS or Azure or GCP, depending on where the data is and who's hosting it. Yeah, but that's all happening, I guess, too. Yeah.
So that's why we're having this experiment. As I said, we've got the high-res versions of the MAG, the gravity seismic. We're trying to see what we can do with MT and experiment, because then you were all talking about joint inversion. So if you've got all the data sources at one site, you can do all sorts of things. And a lot of this data by the surveys and the government agencies is, the usual thing, free of charge over the internet. The issue then becomes that the HPC component, because industry is not picking it up the way the oil industry did, is only accessible through the research community, which is kind of why Auscope's trying this experiment with NCI, because our motto for our project is that today's noise is tomorrow's signal. If you can get at that data at high resolution, what are you going to be able to do? yeah, and see, that's the thing. We've been peddling this. I've actually got a paper which hopefully will come out in preview soon, where we list this experiment, and we have a section where we talk about what the oil industry did. And, you know, how do we get the minerals industry interested in trying this? Because it's interesting, because everyone says, oh, you need big compute because the oil industry's got big data. But the issue is that the geophysics data is higher resolution, and you have more signal to noise problems in MAG, and that I think you can resolve if you get to higher resolution analysis. But anyway, I'm probably talking out of turn, you know me, Helen.
I'm sorry, I'm going to have to run, and I know I'm host, so I'm happy I can just turn off my camera and audio, and I'll leave things going and leave you to wrap up shortly.
Okay. The conversation is quite animated. I can see David has been saying a lot with his mic off in the department there. So I also have to go and do family things shortly. But
okay,
Karen, if you want to,
I'll just turn things off,
going
and then I'll come back and close the meeting later. Okay.
All right.
Thanks again to all the speakers. It's been a great session.
Yeah, agreed. If any of the actual speakers also have to go, you know, we did say 2:30 to about 5:30, but if you do also need to go, and absolutely appreciate that people do have lives, and and sometimes those lives call to us and say, come and do other things. But keep the discussion going as well if you want to. What were you saying, David, when you were not?
Everyone's controlling me on mute here. I was just laughing at Kate because she just loves a supercomputer. I've heard it before. she wants one.
Oh, right. Yes. Well.
Actually, the downside is when you submit a job to the supercomputer, sometimes you wait for a week or two to be run. Then sometimes if you made small mistakes, then you have to fix it, then submit it again. So I think before Michael was seeing he's doing things on his computer for smaller scale, I think that's more efficient for testing small scale modeling. Yeah, not necessarily supercomputer because the waiting time often is too long.
Supercomputer is still just one computer, so you can do that much on it and that's it. Hence, you've got to wait for jobs. So you need another solution if you need something done like now, as opposed to in 3 weeks when the more important people who paid more money are running their jobs are finished and you get to go. So
yeah, it's always.
That's one reason commercial people are not necessarily interested in sharing one with people running their whatever projects and having to wait rather than getting it the next day.
Yeah, well, the trick was to set your jobs off running late on a Friday afternoon or over a long weekend or just before Christmas or something where there's going to be a chunk of time when there's not going to be a lot of people wanting to, you know, apart from PhD researchers. But there are tricks, I think, to getting jobs started earlier.
Don't get data scientists onto these supercomputers because that will just clog up. They will take as much as they can because you can run more and more and more simulations.
In a former life, I did exactly that.
Yeah, so just keep us away.
But the other thing I'll tell you, and this is quite remarkable, because see, for years the oil industry was working on public cloud, or trying to, but then they're very nervous about putting data on a public cloud that, you know, someone could get at it, right, and they lose their competitive advantage. And one group who at the time was very small, Repsol, went to the Barcelona Supercomputer Center and started solving their problems with supercomputing, and it just took off. And if you look at the top 500, which I'm sure not many of you do, but that's the top 500 supercomputer, at least 10 of them are from the oil industry. And some of the bigger ones are from the oil industry. So like once they went to supercomputing, well, of course they got buckets more money than what we've got in the minerals industry. Darwin went and bought their own, which is another perspective on, you know, this study of why is it taken off in oil but not got anywhere in minerals.
Yeah, I mean, we sell GeoClerk into petroleum and into mining, and I think in mining there's much less reluctance to put your data into the cloud and elsewhere. So you might see a lot of that behavior in petroleum, because the question I'm always asked is like, oh, it's a great cloud product, but how do we deploy it into our own infrastructure? You know, and those HPCs are, you know, and supercomputers within their own infrastructure is a way for them to keep everything in-house without anything having to go outside and run it themselves. I think, you know, maybe that's the reason why. I think modern kind of distributed computing allows you to do, you know, build your own kind of supercomputers and run jobs, you know, exactly as you want, and kind of scale out clusters to whatever size, as long as your jobs are written in a way that, you know, can take advantage of that. I think the modern way to do things is that distributed way, rather than having single supercomputers and running jobs on them.
Yeah.
So I think it's technology-wise, I think petroleum, it's just about keeping jobs in-house rather than choosing the best kind of approach for getting these things done.
So are you saying that the mining industry in Australia doesn't want to use, is willing to put their stuff externally, or they're not?
Not everyone, obviously, but far more so than anyone in petroleum. You know, you talk to a Chevron or an Exxon or whatever, and there's just no chance of getting any component, any document, anything outside of their network. They're just completely blind to it.
Yeah, that's the other catch. So I actually wrote a paper it was the 1990s or something, on cloud computing for geosciences. And at the time, everyone said, oh, you know, you're barking up the wrong tree. Mining industry will never put their data on something unless it's in-house.
Yeah.
And going back to the previous decade, as you all know, I'm a bit of an old fart. The surveys used to sell their data, and the mining industry felt it was their competitive advantage on what data holdings they actually had. And as they got bigger and bigger and was more expensive, they suddenly switched on that they couldn't afford to do this. And so this mantra came out of, it's not so much the data that they hold, but the algorithms and what they do with it. And so that became the thing that they locked down.
Yeah, that makes sense.
And then the pressure went back onto the surveys for making their data sets more accessible online. And the thing that stopped them adopting modern techniques at the time was the bandwidth. And that's another thing which I think we're missing or forgetting, is that the research community has access to much better bandwidth than what the government agencies do.
And having worked on remote mine sites,
yes,
you're relying on a satellite feed or something to download data. Yeah, it's not.
Well, that's kind of the partnership that we're trying to promote, and the catch cry is that the government agencies have the data and at full resolution. The research community has the supercomputing and the bandwidth. And how do we bring the two together? I've only been trying to work that out for 20 years, but one day it'll happen, I hope.
Well, we at GSQ, we have our awesome data scientists, David and Kate, working on all these problems. So, oh, good. All right. I feel like the conversation is winding up a little bit. So let's call it a night. Go and get a glass of wine and start making dinner. Thank you to everybody that spoke today that's still with us. That's a few of you. And thank you to our audience members that were brave enough to turn their cameras on and have a chat. It's really great to get the feedback and the participation. And just to the few that are left, don't forget that we have our next webinar again late in May. I forget the actual date, but last Thursday of May, and that will be a series of speakers from international organisations talking about what's the priority in their country and what are the opportunities for collaboration.
Thursday the 26th, Helen. Thursday the 26th.
Thank you. Now that you're here, I just don't remember any dates. Have a great night, everybody, and thanks for being part of our latest webinar. It's really great to see you all.
Thanks, Helen.
Thanks. It was a great
Thanks, everyone.
session.